to understand this applied to the members, which came from ASME B30. In this standard, we found the need for a PEL lift. This lift states that the crane must be able to withstand 125% of the crane rated capacity. Normal crane and Class B light service pertains specifically to Windland due to the crane typically experiencing 3 lifts a day. For the design options of the boom and brace, we considered W sections. These sections give us the ideal space on the top flange of the boom to mount the rollers, as well as structural integrity, or more specific, the resistance to deformation under the intended load to support the shell. These fulfill our needs in the system for our design. To calculate the desired deflection under the applied load, we needed arbitrary members to input into our software. Option 1 were these members, and the total weight was 4 kips. After many iterations in Mass-10, or in our software, we were able to reduce the weight of the boom and brace. By doing so, we ended up choosing option 2, which resulted in 1.9 kips. To calculate the displacement, the vertical displacement of the boom, we use the following. For hand calculations, we use a deflection limit of L over 225, with L equaling 207 inches, and is the length of the boom. This desired deflection limit resulted in a value of 0.91 inches. This limit came from Spanco, which is a company that specializes in manufacturing jib cranes, and this is the limit that they use for their cranes. The software we used to calculate the vertical displacement of the boom from the forces applied was Mass-10 2. This software is a structural analysis program that provides pre-processing, analysis, and post-processing capabilities. Applying the needed PEL capacity of 125% to the load rating of 14 with a safety factor of 3 results in a force of 52.5 kips. Multiplying this force by Spanco's industry standard use of crane equals 31.5 kips. This force is what was used to showcase the vertical displacement of the boom in Mass-10. Before applying this force, we needed to apply fixed connections at the top and bottom of the column. Then applying this force over 120 inches at the end of the boom, which is highlighted in green, resulted in a displacement of 0.58 inches. Based on client requirements, this deflection is under 1 inch and meets those criteria from the client. To verify the results of Mass-10 2, we use another software called SolidWorks. SolidWorks is a solid modeling, computer-aided design, and computer-aided engineering application. Using the same force applied of 31.5 kips and over the same area resulted in a displacement of 0.5962 inches. Using the percent error equation, with SolidWorks being our experimental value, resulted in a percent error of 2.79%. This gave us confidence that our Mass-10 values were correct. The next component considered in the design process were boom rollers, which are mounted to the top of the rollers. These will aid in the rolling process. The first step in choosing the rollers was to decide exactly where the location of the rollers would be. For these rollers, option 1 shows a single row of rollers mounted to the top of the flange of the boom in the center of it. For option 2, the team decided to use 2 rows of rollers mounted to the edges of the top flange. This option offered a higher load capacity due to the increased amount of rollers. The next step for selecting rollers was considering the type of material that the roller should be made out of. The team considered rollers made out of nylon thread and rubber thread. Ultimately, the team chose nylon thread material as shown in this figure due to the high load capacity it offers. This particular roller is rigid and has a load capacity of 1 kil. The last part of the structural members section that we had to consider was the column. We had initially considered W sections to be the column, but after having recommendation from Windland's professional engineer, Jeff Dice, we went with the hollow structural sections, or the HSS members. After further research, this choice of member was due to its significantly reduced weight and high structural capacity when compared to the W sections. It also allowed easier transportation for the carriage along the square structure rather than along the flange and the webbing of the W sections. Having learned mast-end 2 for the brace and boom, we used the same skills for that to choose the best column. Option one was a 22 inch by 22 inch by 7/8 inch hollow member, but was deemed too heavy. After multiple iterations in mast-end 2, we were able to finalize our decision and choose option 2 is a member of 16 inch by 16 inch by 5/8. This option gave the team the best results for displacement while maintaining load passing conditions at not only a reduced cost, but a reduced weight as well. In order to prove mast-end's results, once again, we used SolidWorks. Mast-end gave us a displacement of 0.1081 inches due to the external force applied of 25.26 specifically from the boom and brace. The arrows depict these forces applied through the carriage and into the column from the boom and the brace. And as stated earlier, there are fixed connections at the top and bottom of the column. With this criteria, SolidWorks resulted in a displacement of 0.1043 inches and gave us a percent error of 3.52%. This again gave us confidence in mast-end's values. Matt will now discuss the carriage.
Thank you, Jacoby. I will now discuss the carriage components, calculations, and analysis. The carriage is a system component which provides the ability to travel along the column vertically and also a mounting location for the boom and brace. Carriage components include the pin flange with pin, the rollers, and the emergency latch. To design a pin flange capable of withstanding the forces applied to the boom, as previously discussed by Jacoby, we use mast-end 2 and set boundary conditions at the locations of each pin flange. By recording the reaction forces at each of these locations, the top flange has a horizontal force of 25.26 kips and a vertical force of 22.63 kips. For the bottom flange, we have a horizontal force of 25.26 kips and a vertical force of 54.13 kips. With these values collected, we could then move on to hand calculations. By applying the horizontal force of 25.26 kips, we could use that as a tension force on a flat plate with a hole. By calculating the nominal stress of 1.23 KSI at the smallest cross-sectional area, 2.25 square inches for our design, we then had to calculate the stress concentration due to the hole being present. We used the analytical method as seen by the equation with KT, and we calculated that value to be 2.42. By multiplying this value with our nominal stress, we calculated a max stress at the hole to be 27.17 KSI. By simulating the same design in SolidWorks with a material applied at 4340 normalized steel with a yield strength of 103 KSI, we got a max stress of 28.3 KSI at the hole. When compared to our hand calculations of 27.17 KSI, we calculate a percent error of 4%. With confidence in our FEA, we can now apply these forces to our pin flange design. With the horizontal force again as 25.26 kips, we get a max stress of 24.8 KSI on our flange. By applying the same force to the pin that will be inserted into the flange, we now have a shear force of 25.26 kips. This is considered shear force on the pin due to the force being parallel to the pin surface, resulting in a max stress of 79.9 KSI. As stated previously, with the vertical force on the top flange of 22.63 KSI applied to our top flange, our max stress results in a 73.35 KSI. And finally, for the bottom flange, our max stress, our vertical force of 54.13 kips applied to the bottom flange provides a max stress of 129 KSI. As you can see here, our design does fail. For this reason, we add reinforcement between the pin flange and the gussets, reducing our max stress to 87.272 KSI, making our design pass. The next component I will discuss are the carriage rollers. These rollers are mounted between the carriage and the column, providing a rolling surface for vertical movement of the carriage. Our design implements 2 sets of 4 rollers. The first set is at the top for the pull force due to the boom. The second set is for the thrust force caused by the brace. Now, unfortunately, our carriage structure was not, the analysis of our carriage structure was not complete, but we thought it was necessary to choose an initial component for these rollers. So by using the horizontal force applied to the pin flanges, we applied the external force of 25.26 kips equally among the rollers, resulting in a radial force per roller of 6.32 kips. We believe that these forces will increase whenever the analysis is complete for the carriage, so therefore we selected a roller with a dynamic radial capacity of 22 kips. Like the carriage, the emergency latch analysis was also incomplete. Although we did make a design incorporating a lever arm and sawtooth design, where the sawtooth is mounted to the column and the lever arm attached to the carriage. In the event of lift system failure, the orange pin, as seen here, will fall, while also causing a torsion spring to actuate the lever arm, engaging the lever arm with the sawtooth design. I will now speak about the lift system standards, calculations, and design options. The lift system components include pulleys, hydraulic cylinder, and wire rope. OSHA standards considered pertain to safety, where pinch points and wire inspection apply. Although the team initially performed a review of components, I can't remember the word. Although we performed literature review on electrical and hydraulic lift systems, after speaking with the customer, they prefer hydraulic cylinders, so that's what the team proceeded with. Prior to component selection, we needed to calculate segment tensions for all scenarios. During static conditions, as you know, all segment tensions are equal, but during moving conditions, these segments increase gradually while moving away from the carriage. This is due to the friction forces at each pulley, and 2, as seen here, we have a pulley with a hydraulic cylinder applying pressure to that pulley, and this causes the hydraulic force to be split between each segment on either side of this pulley. With this in mind, and a static coefficient of friction of 0.3, with a kinetic friction coefficient of 0.15, we use the equation below to calculate a max moving segment tension of 25.76 kips. Once all segment tensions were calculated, the team was able to select a hoisting component, and due to the high loads, the team selected wire rope due to the strength to weight ratio. With a max segment tension of 25.76 kips, the team selected a wire rope with 1-inch diameter with a minimum break strength of 144 kips and a safe working load limit of 28.8 kips. As mentioned previously, the hydraulic force is divided among the two segments on either side of the pulley. This implies that the hydraulic cylinder must be able to withstand the summation of those two tensions. The table shows these summations for each scenario. As you can see, with the selection of a hydraulic cylinder with a column load capacity of 30 kips, our selection is capable of holding at all scenarios, and it's also capable of holding the dead weight, which is the carriage, the boom, and brace when unloaded. Nathan will now speak about the prototype.
Thank you, Matt. So for the prototype, I'll be going over the scaling, I'll be going over the analysis and testing we performed, and lastly, I'll show our demonstration. So a few point of interest we would like to show on our prototype. The first one is the pin connection. The pin connection is how our boom and brace attaches to the column. Another point of interest we would like to show is how the rolled sheet comes in contact with the rollers during our plate rolling process. Before we actually started building our prototype, we decided to perform a finite element analysis on our pin flange. This was to validate the cross-sectional area and the design of our pin flange at a half scale. The external load we applied here was 56.2 kips. This load is actually the load capacity of the universal testing machine that we will be performing our experiments on, mentioned in the next slide. The result of this analysis gave us a tensile test of 54.6 KSI. For experiment 1, the team performed a tensile test. We did this to validate our cross-sectional area and the overall design of our pin flange. The parameters of our pin flange include a plate thickness of 1/4 inch, a pin diameter of 3/4 inch, and a force applied of 56.2 kips. The results of experiment 1 are as shown. Here in this graph, we were able to find that the force at which the pin flange broke was around 42.9 kips. The recorded tensile stress of the pin flange was 54.85 KSI. When comparing our experimental value to our SolidWorks value, we calculated a percent error of 0.091%. For experiment 2, the team performed a fatigue test to validate that the design of our pin flange can endure a life cycle that is satisfactory. The parameters for this pin flange include the plate thickness being 1/4 inch, the pin diameter being 3/4 inch, the number of cycles or the amount of times our pin flange endures loading and unloading is 1.0 times 10 to the 7 cycles. The stress applied, which was 4.33 PSI. This is by taking our scaled force and dividing it by our cross-sectional area. The results of our fatigue test, we performed we attempted three different fatigue tests on this machine. Our test 1 was using our half-scale pin flange. This resulted in the cooling machine overheating and the last observed value only being around 2,000 cycles. For test 2, again, we used the half-scale pin flange. The result of this, the program had crashed this time. However, the last observed value for the number of cycles was around 26,000. For test 3, we changed from the half-scale pin flange to the full-scale pin flange. This was because we found that the UTMs was capable of our full-scale load. However, the program had crashed as well, and we only observed around 1,600 cycles. Although we were not able to fully complete a fatigue test, using test 2 and assuming our pin flange fails around 26,000 cycles, we were able to calculate the lifespan of the pin flange to be 33 years. So although we used half scale for our testing that I just mentioned, we found that when our prototype was half scale, it was actually too large to be in the Hunter Strain lab. With that being said, we further scaled our prototype to a 5th scale. This would also allow us to accommodate the roll machine in the Hunter Strain lab. From there, after we scaled it, we proceeded with manufacturing it. For our deflection test that we want to perform on our pivot crane, we started by setting up the dial indicator at the top of the boom, as you can see here. From there, we measured each of the 45-pound plates to have a more accurate result, being that they weren't always 45 pounds. Next, we distributed the weights along the boom accordingly and recorded our results of the deflection. The goal of this test was to validate that the deflection reflects our analysis. For experiment 3, we performed a deflection test to validate our crane deflection at a 5th scale. The first test, we applied a force of 47.311 pounds. This resulted in a deflection of 0.0960 inches. The next test we did was applying 97.771 pounds of force to our pivot crane. This gave us a deflection of 0.1620 inches. Lastly, increasing the weight, we applied another force of 135.811 pounds. This resulted in our pivot crane deflecting only 0.2690 inches. To validate our experimental pivot crane deflection, the team decided to perform finite element analysis on the pivot crane, matching our experimental conditions. The first analysis we performed was applying 47.311 pounds to our pivot crane. This resulted in a deflection of 0.0904 inches. The next analysis we did was applying a force of 97.771 pounds, resulting in a deflection of 0.160 inches. Our last analysis we did was apply a force of 135.811 pounds, and this resulted in our pivot crane deflecting 0.2460 inches. When comparing our experimental data with our finite element analysis that we performed, we were able to calculate a percent error of 5.6%. In this video, we are showing the rolled plate coming in contact with the rollers. As you can see here, the plate is smoothly rolling over the rollers without any issue. For our next demonstration, we are focusing on the locking and pivoting system. In the video to your right, you can see the pivot crane going from its stowed position to its operating position. Taking a closer look at what's happening is our locking mechanism. This is done by the operator pulling on a cord and engaging and disengaging the locking pin. So for the conclusion, we'll be going over the cost and risk analysis. We'll be going over our improvements, and lastly, talk about our project results. For the cost analysis, after completing this project, we were able to estimate the full-scale pivot crane to cost $24,821.26. We found that our 5th scale prototype cost $222.93. And here's a picture showcasing both of those.
So the risk analysis we need to consider for the full scale. On the table to the left, it shows these risks in order from most dangerous to least dangerous. The weld imperfections and the wear of the hinge joints between the boom and the carriage are deemed most dangerous due to the fact that if they fail, the boom will fall to the ground, resulting in serious bodily injury since there will be no catch implemented into the design. For this reason, there shall be an inspection once a week for the jib crane.
To conclude our results, we believe we've proved that the deflection of the boom remains within the limits specified. The percent errors between FEA and hand calculations provide us confidence in FEA. The design lift system is capable of moving under no load and holding at all scenarios. And finally, the percent errors between experimental values and FEA provide confidence in our design. We believe, with all of these considered, the crane system meets client requirements. The team wants to also recommend for future work, potentially implementing lubrication lines to reduce friction in the lift system and at all pulleys and increase wire rope life. The fabrication of a lift cylinder housing for stability against lateral forces, an in-depth analysis of the carriage structure and forces on rollers, an analysis of existing foundation and structural support as discussed with the client, finishing the development of the emergency latch system and analysis, and finally finishing the development of the pivot latch system and analysis. Finally, we would like to acknowledge Dr. Hamidi for her help throughout the last 2 semesters, and Mr. Gravely for helping us in the shop during those late hours in the shop. We also want to thank the faculty and staff of the engineering department and thank Winland Manufacturing for this opportunity. This concludes the presentation for Rams on a Roll. Thank you. Any questions? Yes, ma'am.
When you say the program failed, when you're at the, you just reach the limit of what it was able to do? Is that what you mean by that?
There were a couple of them. We just picked the one that we had some observed values recorded. In one instance, the computer just shut off. In another instance, the program just said Blue Hill stopped working. As for the other one, as for the other crash, as Nathan specified, the cooling system did fail once, but David was able to get that fixed at the last minute, and we were able to proceed. But unfortunately, we weren't able to do a full fatigue test.
Just interesting, yeah. And I like the mechanical pin that you used. I think that was a really good solution on that. You know, and the other question I have is on costs. Because how you calculated your costs. Of the actual, yeah. That's a big one we always miss on, because it didn't cost you $222 to make that fifth scale. I can assure you, it cost you a lot more than that. And so for the full scale, I'm sure it would cost, and so I'm just curious how y'all calculate that.
What's included and what's not included?
And what's included, yeah, because that's not labor and all the other.
For the fifth,
I would guess that would be around 75 to 100, but anyway, that's just, yeah.
for the fifth scale?
No, or either, for the full scale, either one, how you got to those, because those are so important. Cost is every, when we do projects,
Right.
costs are the biggest thing we have to abide by, so.
For the fifth scale cost, we only considered, all the components. However, Winland donated the, boom, brace, and column, so those aren't in, the fifth scale cost. However, everything else is.
Labor,
Not labor.
no, because
Oh,
I'm trying to get you
Yeah,
to
we're more concerned
costs.
about the full scale
The
cost.
full
What-
scale,
oh, okay.
yeah,
What's
the
in the
cost of
full scale
project.
cost and what's not?
Yeah, what's the cost of the project
we have
versus,
the-
yeah. Because you've got, there's so much, I mean, that is huge, we have to be able to, yeah, it's not just,
Let us go to that.
yeah. It's just, we, as engineers for design, that's the biggest thing, we get, cost, and you have to look at the whole, yeah. So
So
those,
this is what we estimated our full cost.
yeah. But you had like labor and,
No, ma'am.
and,
No, it's not
and
work.
handling
This
and
is all
all
just-
the other, yeah, cause welders are expensive.
Yes.
Yeah, it's material cost is what you've got in there.
Materials,
That's okay,
yes,
very
ma'am.
good. That's what I'm trying to get at. So maybe look at a bigger picture of the true
Okay.
cost.
Okay.
Because, you know, I mean, hours and hours of labor, especially welders and people like that, because what it's gonna take to build that,
Mhm.
that's a lot of expense, and it has to be calculated in as we calculate payouts and all the other things involved, but
Mhm.
great design,
Yes,
but I
ma'am.
just, yeah, cost, because the last time, that's one of the things we're not picking up,
Mhm.
and that's important to Winland, everybody that's gonna look
Yes.
at this, it's not gonna cost them 24,000, it's gonna probably cost them.
Right.
I think it's real important to, when you give to put what the basis of the cost is in it.
Yes.
And the other question I have is, are you sure it's $24,821.26, or is it 27?
Did you pay taxes, and did you pay the
Okay,
taxes?
so what's the point,
Okay.
so what's the point?
Yeah,
What's the point of that question?
We could estimate, we round it up to 25,000.
Yeah, it should be like
Order of magnitude.
25,000 or something
Oh,
like that.
okay.
I mean, that,
I think some of those came from the exact values from.
well, no, I understand you built
Yeah.
it,
yeah,
but in terms of an engineer presenting this number,
right.
it's like 25,000, and that's material only without
Right.
fabrication costs and delivery and, you know.
Okay.
Oh, because delivery would be outrageous out here, I can tell you that after working at the conference, you can deliver, I mean, all that stuff, yeah,
so.
and they can do a lot of
And
that,
similar,
yeah.
similarly with your, prototype costs,
Mhm.
it's not very, so it cost me, as the chair, 200, and whatever the total was, which is great, I really appreciate that you got Winland to donate the funding, but that's not, even excluding labor costs, that wasn't the cost of the prototype. And you could have, I mean, you knew the value of what they donated to you, right?
Mhm.
So I would have done, I mean, I would have put
Okay.
the total material cost that you did, and then if you were gonna break it out, you can put down what was purchased and what was donated, but that's still a cost, even though it was donated, right?
Yes, sir.
Just somebody else paid for it.
Mhm.
And while y'all have a lovely machine shop over there that we do have here, that costs money, because I just finished patenting a product, I have to go rent a machine shop to manufacture my stuff. That machine shop costs money just to walk in the door, and your labor is labor. It's all, and that's, what these are all costs that get involved in doing, yeah, and then we have to really look at as we get into it, because that's the first thing your bosses are gonna ask you too, is the real costs.
Okay.
So you have to, yeah, so anyway, just,
Yes, ma'am.
yeah, it's one of my, because I've been beat on it for 45 years, I've
Yeah.
done, yeah, this is, yeah, so thank you. Thank you.
Thank
And because the other thing is, welders and people at these skilled professionals are expensive,
Mhm.
as for reasons they are, because they're skilled professionals. And plumbers and electricians and mechanics and welders, it adds up in a hurry nowadays, yeah.
Yes, ma'am.
So.
Yes, sir.
I want to come back to your fatigue test. You said you estimated a life of 33 years.
Yes, sir.
How did you determine that?
So we took, we assumed our pin flange failed at 26,000 cycles, and knowing Winland does 3 lifts per day, we multiplied 26,000 by 3 by the number of days a week, by the number of weeks in a year, and calculated lifespan of 33 years.
And then with, in that, what is failing in that? Is that the plate that's failing, or is it the pin?
The welds, what fails at that point?
For the fatigue test,
Yeah, in the fatigue test.
the
What was the
we're
expected
testing
failure?
the actual, flange, so the actual plate would be the failing component.
The plate with the hole in it?
Yes, sir.
So I guess the follow-up on that would be, at the 26,000 cycles when it failed, did you guys see fatiguing at that point that you might have been able to then estimate had you been able to go 50 years or so? So at 26,000 tests, what kind of wear were you seeing to then justify using that as your failure point? You might have been able to say, okay, at 26,000 cycles, we've seen X amount of deflection or fatiguing. At what point do we anticipate that it's no longer going to be able to be usable, and then maybe estimate out a little further on your overall life expectancy?
Yeah, it's really conservative, but, you know,
Mhm.
I mean, why,
Did you see damage?
We didn't see any damage. We did put a light through it. We didn't unfortunately take measurements on the eccentricity of the hole. We can still do that and provide that, but, no, we didn't take any measurements or see any damage to the pin.
so why did you stop at that point and decide that was a satisfactory analysis?
We stopped at that point because the UTM,
No, when you took the,
oh,
when you went from 26 I'm not criticizing
no,
here, I
no.
wanna know what, when you went from 26,000 cycles, said, okay, we're just gonna use that to estimate the life. I mean, why didn't you then go on and say, well, you know, a better estimate based on, cause it's obviously gonna last more than 26,000
Right.
cycles, so why did you just stop there and say, we're gonna take that as the life?
Because that was the last observed value, and when the machine crashed, there was no data collected. So we
Well, I mean,
couldn't-
that's not the question I'm asking.
Right.
So you only got 26,000 cycles,
Yes.
right? And you said, okay, well, we're just gonna assume that's failure, we're gonna go from there. And why did you decide that, and then you predicted 33 years, yada, 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 right? Why did you stop there and decide that was okay? Why didn't you go back and say, well, it's really not 26,000 cycles based on, you know, we really estimate it to be long? Why did you stop at that point and say that's a good enough analysis?
After doing literature review on the typical lifespans of jib cranes, we found that 33 years fell within their minimum and maximum, so we believe that was an okay place to stop.
Yeah, I mean, we do, the reason I'm asking this is, we do lots of things as engineers where we don't know something, we're estimating something, and we do exactly what you did, which is say, well, I'm gonna take what I know and see if it matters.
Mhm.
And the answer is 33 years, that's fine, doesn't matter, right?
I see.
Right, and so I think you're not,
See,
I mean, people are saying, well, why don't you only use your size, and why don't you do this? Because the answer is, because we got 33 years, and that's satisfactory, we don't need to go any farther, and it's conservative, right? And so, because we do this all the time,
As I
right?
said, I think that's one to your point, that's one thing, as you gut feel, a lot of the stuff, you do that, and you verify it, and the more you do it,
Right.
you learn it is just, okay, that's, yeah.
Meets the
what-
So,
That means.
I mean, if you came up with,
yeah,
if you
the
came up with 10
standards.
years, now you got a problem, you're gonna have to do something, right?
Yeah.
But when you come up with 33 years, and I don't know what, did the client give you an expected lifespan,
No,
a design lifespan? Okay, so,
Did you consider any safety factor for environmental corrosion?
not for environmental corrosion specifically, with a safety factor of 3 on the structural components. We believe that to be conservative, so we could go back and look to see if that is.
Do you propose
Sufficient.
any maintenance check for daily basis or weekly basis?
Yes, Jeff Kobe mentioned that it should be checked weekly.
Like what parts do you need to check, the weakest part?
Specifically, the lift system, the pivot components, the pivot flange, the critical components that we discussed during the presentation.
Yeah, the environment's not caustic or anything over there, I know what you're talking about, because I was over there with that, so I'm not sure environmentally, but there is routine maintenance, obviously. That has to be done as part of.
I had one other question, on the deflection of the beam and the position of the rollers. As the beam deflects, did you find that it would, at some situations, break contact with some of the rollers and possibly cause an offset into the manufacturing process of the twist on the plates, if it was only in contact partially?
Short answer, no.
Okay.
But due to the rolling process, these shells do tend to not be round the whole way through the process. For that reason, we believe that any deflection in the boom, the material would fall off.
I think in one of your videos, you showed it, because it kind of rippled one of the edges.
Yeah, that ripple actually
That's a normal,
comes
that's a
from-
normal part of the rolling.
Yeah, the roller in the
process.
shop does pinch at the
Yes.
end.
And that's part of it.
Yes, ma'am.
And how do you calculate error? So I see there are many calculations for the error. Sometimes they compare your results with the experiments, or sometimes they compare with your simulation results with your calculations. So are they reasonable? Were they all reasonable? How did you compare your results? Or was there any information in the literature that you would find to compare your results with the
Literature,
Are
as
you
far as
reasonable?
percent errors, no, but, through all the classes we've taken, percent errors below, around 5%. We're confident in, accepting. As far as the hand calculations go, there were a few times that we got upwards of 10%, and we had to go back and look at our hand calculations and recalculate, because we did have a few things wrong. But as far as literature review for, percent errors, no.
While we're on this slide, am I interrupting? While we're on this slide, You measured deflection only at the end of the beam, is that correct?
Yes, yes.
So, how was the prototype, column attached, and how do you know that the boundary conditions that you applied in your FEA are correct? Because I don't think the prototype was attached that way.
Glad you asked, because we thought about this as well. We're restricted with time constraints. For the FEA, the boundary conditions were at the floor, as you can see on the picture on the right.
Right.
But for the prototype, we manufactured a clamp
Right.
to clamp to the roll machine. One of the tests that we wanted to conduct was to include another dial indicator at the base of the column to see if that would also reflect any deflections on the end of the beam, but we just didn't have time to complete that.
Because boundary one of the big
They do have.
sources of error in any of these numerical analyses is the boundary conditions.
Mhm.
And those aren't the boundary conditions that, I mean, it's an okay approximation to the boundary conditions, maybe, but I mean, I think that would be really critical to do if you were gonna, extend this test to. And then can you go to the chart of the loads on the cylinder? And comment about the red numbers?
Yes, so,
Cause you just blew right over those.
yeah. With the hydraulic cylinder applying pressure or applying a force to the pulley, and that force being distributed equally among the tensions on either side of the pulley. This this indicates that the hydraulic cylinder needs to overcome the summation of both segments. And what this table indicates is those summations. So at holding a hydraulic cylinder of our selection with a column load rating of 30 kips, we're able to hold at all scenarios.
Right.
And the moving scenario of the dead weight where no load is applied, it is able to lift the boom vertically along the column.
Right.
So we're okay, but this just indicates that they should not be lifting any loads at the load rating or at a planned engineering lift with the lift system.
Okay. You think, what's your, professional opinion is, soon to be engineers about that? It's gonna fail if they either try and lift during a planned engineering lift or even at the loaded rating, right?
And fortunately, there are companies, consultants out there that dedicate their whole career to planned engineered lifts.
Right.
So in the event of a planned engineered lift, we would recommend Winland Manufacturing to consult with
Okay.
a consultant and develop. a
I'm way more
process.
worried about the loaded rating one though, because they're not gonna do that for the loaded rating necessarily, right?
Luckily, at this moment, this is the load rating. We planned this design for future bigger projects by Winland Manufacturing. So luckily, at the moment, the largest capacity is 10,000 pounds, or just over around 11,000 pounds. So with a load rating of 14,000 pounds, we don't believe this would be an issue, but we are gonna address that in the report.
So would you change the load rating of the?
Well, we don't want.
I mean, how would you propose dealing with this? See, it sounds like you're not proposing changing the design. I'll ask you a question about that too, but assuming that, cause you're saying, well, in in most operational situations, it's not gonna fail.
Right.
Okay, so how would you, as an engineer, how are you gonna, if that's your stance, how are you gonna how do you think you should deal with that? Cause it doesn't meet neither the planned engineering lift or the loaded rating as you've rated the crane, does this component meet I realize the operational things, it's not supposed to be moving, right? It moves in, you put it in place and it's not supposed to be moving.
Right.
But that doesn't, so how would you deal with this as a designer?
I would either change the lift system or reduce the weights or at the moving brace and the carriage.
Those would be the safest things. You could also do operational constraints too, right? So speaking of changing the system, just conceptually, how, what alternatives, this is very, very common. You get into this project and you get to some place, you're like, dang, this isn't gonna work for this one thing I didn't think about, right? So that normal, and for a capstone project, no problem, great, you recognize it, you skipped over the presentation, but, all right. How would you approach, changing the system? What are the conceptual things you could do that would change? That would improve this?
We could change the way, instead of using hydraulic cylinders, we
Okay.
could use a hydraulic winch, we could use electric motors.
Okay.
There's multiple different ways, but we did go with the hydraulic cylinder.
Yeah, no, that's fine, yeah, I'm just asking you how you might approach this. What about just putting it so it's in tension instead of compression?
The hydraulic, we did do some research, and the hydraulic cylinders tend to have more, push force than pull force. I don't know, maybe that's.
Well, I mean, I'm just
I
talking
don't know if I
about, I'm
understand
just
the
talking about putting it in a geometry where instead of the cylinder being being in compression, where you can have a buckling problem, you put it in tension, and you don't have any buckling,
Okay, I
right?
see what you're saying.
I just wondered if you thought of that.
We did not do that, no.
Yeah. That's the first thing I thought of when I looked at that, I said, wonder if you can put that thing in tension, and we don't have to worry about this. So, I mean, there's,
No, that's
it's,
good.
it's gonna complicate your design a little bit, but it's an interesting possibility.
Any more questions?
So I'd like to know, outside of the presentation, the technical stuff and all that stuff, what are your big takeaways from having completed a Capstone design project? What are the, I don't know, three most important things you learned in this whole process?
Teamwork, scheduling, and sleep.
And that, you're going for it?
Yeah, research, sleep is a big one, and, just putting the time aside to apply everything into the capstone.
Okay.
Cause this project has taken a lot of time just to get it built as well as do the research for it.
How did your scope change during from the beginning of it to what you actually were able to accomplish? And I'm not complaining about what you were able to accomplish,
No,
that's not a criticism.
It definitely started like, what's it called? Initially, we thought we could do a bunch of things in our scope, and then gradually, as we were going through the semester, our scope just kept getting more defined over.
Yeah.
Thankfully,
Well, I like the way you bring that up, and it is actually, you didn't say it got smaller, which it did get smaller, but actually what had happened, it got better defined,
Yeah.
right? Yeah, and I think that's a really big lesson, right? Because you're not gonna have the luxury in a commercial job to like drop off a bunch of the scope because you didn't figure it out in the beginning. So I think that's a really great lesson to have learned, so.
Do y'all think you're gonna like being engineers now?
yes.
I've been doing this for a long time.
As opposed to an engineering student.
That's the best thing ever when you graduate. Have you taken your engineering training exams or what fundamentals exams and are you getting your licenses? Very important. So now that you're graduating as engineers, please get your licenses.
Yes.
It is critical. We have a shortage of licensed engineers in this country like crazy.
Yeah.
And we need licensed engineers, so please, and so keep up the good work.
Man, keep saying that,
Yeah.
please.
Yes, please, because we have such a shortage, and especially talented ones that need them. Yeah, so-
Especially in San Angelo.
Oh, God. Yeah, there's what, 3 of us?
Yeah.
I think 3 in the whole city, yeah,
Yeah.
and, yeah.
I did wanna say that we're gonna be headed over to the Hunter Strain if anyone wants to see the prototype being used. We'll be there for 45 minutes to an hour.
Oh, there you
Yes,
go.
ma'am.
I did want to mention that I said in the presentation last semester when your project was an idea phase, and I just want to commend you all because your confidence from then to now has greatly improved.
Thank you.
And Matt, you have great leadership skills because even from the mock presentation last Friday, I could tell you were deep down, but you turned it around, and whenever you showed confidence, your team followed. So I commend you on that.
It's a huge, you guys did a tremendous amount to make improvements to the presentation in the last 2 weeks, so congratulations.
Can I get the floor?
I apologize, I think we missed the first 10 minutes of your presentation. So, I thought we went live, we did not go live. How's it going? Good to see you. For those of you online, we'll be back at 1:15 for the next presentation.
Yeah, I didn't have to be, well, they start, I was like
So then I was
doing the whole
like
thing all
trying to
the
check
time.
my phone, and then I forgot.
Hey, did you find it? Okay, perfect. They have, they're not gonna start it for another 15 minutes or something, but I'll see you. It's upstairs. You'll find us.
It was the best.
Super. Glad you made it.
You got the clicker? Yeah. Okay, I'll put it over there. Awesome. Thank y'all for showing up.
Absolutely. Wouldn't miss it. Well done.
I'm trying to scoot back.
You persevered through all the criticisms. Very good.
Criticism
Jim,
isn't
sir.
the problem. Understanding
Yeah,
questions
well,
is the
you-
problem.
In the middle of what you were, whatever you were saying. Yeah. Had it on airplane mode, it had the volume all the way down, I don't know.
We need a lot of everybody. Come on. You want my problem? I'm licensed in here 44 years. Come on. I'm serious.
Thanks for coming.
You need more So how, us, the things are there's only three of us. There's more things. Oh, yeah.
So, you think this probably isn't gonna be in the camera?
I don't think the city.
Yeah, it is.
It's in camera, okay.
Yes, it's in.
Yes. So Erica Carter, what do you do? She does it. And then I have several attack dogs. There's no women, there's no licensed women attack dogs. 9 years.
Yeah, I'm done. Thank you.
He's gonna go.
Come on. Let hire us old people.
Hire us all. That's okay. You got a lot more experience than I did. Thank you. My office is on the north side.
Good, yeah. I just realized this morning.
That's better.
I told you guys I would. And then I realized after I put it together, these short term.
I'm not on Airwalker. I run the Armstrong. On the north side. Armstrong and 28.
you're gonna make, I love maintenance, okay, my husband's a general contractor, so we built buildings and all, I love it.
Yeah. It's always something new.
It's not as good as
Yeah.
Yeah.
Yes. Yeah, so I'm all.
I mean, if you can't, you can't.
I just had a summer on mechanical engineering, so. No, we don't discriminate. How are you? Good to see you. Good. Busy, very busy. Always. Busy, very You showed me last time.
Yeah, we heard something. So do what we did with the Capstone. Oh, wait, that's not coming up.
I like it.
And then we were hosting.
I mean, like them too, like, I was wondering how much It's just scary. That's true. That is true.
You probably don't need to be advocated, or definitely not.
Yeah, literally. Are you taking the whole thing?
There we go.
Oh, no, I about 10 minutes. I was stuff. You can't take the whole? Yeah. But I mean, these are mechanical. Yeah. This is a mechanical. But it is pretty cool.
No, I do probably wanna stay with part of it.
Well, this, yeah. This one, I want the paint, yeah.
How we doing? Good, how are you? All right. You behaving?
I'm just sitting back here taking this. These are mechanical. I'm gonna wait till we get to the civil one and then.
Yes, she's saving her.
I'm saving all my questions. I'm just gonna hammer Drew Dykes.
I think she's saving that.
Yeah, we got 3.
Keeping her powder dry.
That are on there. I gotta save up all my questions.
Hey, I have a really interesting question. So we were doing,
Our subscales from the chiller. Brought the subscale out. Not in Region 6. Yeah, we still got a lot. We feel pretty good. Worked out really good.
in fact, and then I go into witness questions. We actually. Pretty good results. So the quick, This will say this. Focus groups with students and that, this is one of the biggest things you got going for you. Almost a lot more power. This one's
Rules state it's only set out for 2 hours. So they let us use our backup. Almost all the rockets that they read that long.
Well, there's so much it's really cool. So I asked one of our at that point, we were on the had an extra, and the extra ended up. I just think it's, I think more in sports, the value of money is, thank you. This question, this might take it easy.
I was scared.
Because the next one, so we're working on really hard to transfer. My next target is the NFTs from our region. Those ones, we're gonna have it. The transfer, I've got it.
Are you willing to coach the
It
others?
might be, it has to be something we have.
Yeah.
I just wonder if you could just even. It wasn't like. Yeah. Well, I'm not saying, yeah, I'm not saying you know that they did. Yeah. I got you. There must be some way you could. I'm not just saying, so, this is probably just a way to do it, but like if we reduce that by 20%. There was different ones that, and then, like, go
This is sad, and then the high goes over here.
Yeah. But like this strip of Dallas, I think we definitely got these ones.
Because you.
I mean, I don't know what we're Well, we got our fishing ponds big over there. But we only need, I mean, there was one that was like, I only have 20. We could if I could do, I just did my first one thing is people like you, and I made my goal. This is another thing. Like we have, I mean, Dodu said this. You guys are asking us all this stuff. How come I don't have?
I don't like any
It tells me. Because I was kind of toward the.
Rest a lot.
Last time I asked for something, there's cognition reports, go out and figure it out. Yeah, but you can figure it out. He's right, I can't. I spent, I spent 16 hours. Cobble together the cognition reports, and it works until the cognition reports change, and then they change, and then it doesn't work. How come I don't have a dashboard to show, how come I don't have a dashboard that tells me what my production costs, my estimated production costs?
You guys are ready, you're gonna launch now?
Yeah.
You're gonna show us a demo or just?
We have a video, we just brought this over. We have a video.
I mean,
We're pretty cool. We brought in our
Like, our fall vacation numbers, we calculate from the federal, like useless. That's not the number of
I know we have a real one here that's just in the, but I don't know if we have.
not just
that's a,
I push my numbers up, just like, that obviously is what I said.
I mean, I'm just saying, like,
Well, that's not what you're reporting I understand, they have to the ways to find.
You got another wire, we can power on the battery.
That's not the number I care about. Yeah, I hope this works out. I think there hasn't been enough time to, every insurance meeting. But is it about, what are you doing?
Little trigger, it sends that pulse and matches that, and that powers on. I need them. So it would technically, if we power it on, it matches it in 2 minutes. You can't.
Oh, yeah. Too busy. Yeah, man. This semester was, well, I went on 3 trips, which is like 2 more than I usually do. And it kills me because I mean, half of my time is supposed to be spent teaching. Yeah, that'd be like you spending half your time actually doing interior design or something, and that's it's like crazy. Well,
Either that or the radio club.
we had a real interesting meeting. No,
the whole.
You realize that when you're at the desk, really manage your program and, do the numbers. I mean, even the resources you have to manage in most programs. And so they don't think strategically, they don't plan ahead, they don't think about the next 5 years. And then now they're starting to say, hey, what do we want to do? Well, some of them do, because they didn't
Yeah, that's.
Some of them would. And when am I gonna do that?
I'm not gonna add those duties to what I'm doing.
I had to do it from the beginning, because I was old. And you know, my kids are all gone, workaholics, so. But I'm getting to be into that rope, baby.
There's days I get up, light goes off, I'm looking for my motivation.
Won't be able to make the PS class, I'm not sure about it.
Yeah, I'm hitting that,
But I did it right.
I'm hitting that retirement milestone really soon.
You know, we have not had
They are, this for the summer ones or for the full-time?
permanent ones, because we can do full-time summer and part-time in the school.
You're talking about the interns? Yeah, they have multiple opportunities. Yeah, you're not the first person. Hey, why do we have to? Oh, 'cause they got it. I'll push it one more time though, yeah.
I'll send something over to you separate.
Okay. You gonna do a quick
Okay, yes.
introduction?
Yes, first of all, thank you everybody for attending our Capstone Design project presentation in spring 2022. So our first team, I think they did well. This is my second team from mechanical engineering, and they did a very good job. Actually, they prepared for competing in the NASA launch competitions. Therefore, they made a rocket, and there's also senior design project is about what they did here, so we kind of maxed them. And I think it was 2 weeks ago, they successfully did the launch in Alabama for the NASA competition. So I leave the stage to them to start.
So, good afternoon, everybody. On behalf of the Rams and Rockets team, we'd like to present to you our project. Starting off, I'd like to introduce myself. I'm Antonio Arriola. I'm the team lead for this project. We have Zachary Goodman as our project manager, Chad Lutweiler, our safety engineer, and finally, Patrick Nash as our project engineer. This is a quick overview of our presentation. We'll be going over just kind of the scope of the project, kind of revolving around the NASA student launch competition, our launch vehicle, also including our recovery system, our payload overview, kind of discussing the components, how we got to where we got to, our subscale results, our full-scale results, kind of our cost analysis, and our conclusion. From here, I would like to pass it on to Zachary Goodman for the scope.
So I'll kind of talk to you all a little bit about what NASA Student Launch is and what we had to do to meet the accomplishment of competing. So the NASA Student Launch was hosted by the Marshall Space Flight Center in Huntsville, Alabama. It consisted of middle school, high school, and college level teams. There was a total of 69 students teams that competed. Students were tasked with designing, building, and testing a rocket and a payload using the NASA design method. The rocket and payloads were tested on April 13th through the 15th, and the students were required to meet all specified timelines and provide all submittals. So some of the requirements, students had to do 100% of the project. In addition to that, we had to do direct STEM engagement with 250 participants. As far as the requirements for the launch vehicle, we had to deliver a payload between 4,000 and 6,000 feet and then land the rocket safely. The rocket had to be reusable, and the vehicle must not exceed the speed of sound, which is 767 miles an hour. And we had a drift distance, a maximum drift distance of 2,500 feet. We had to keep it within that distance so it didn't go into private property that NASA did not have permission to be on. As far as the payload was a camera system that received radio frequencies and then performed actions based on the packets that were sent. So the NASA timeline was very fast. All the submittals had very short spans between each of them. We had about 2 weeks to do our proposal. From there, we had a preliminary design review to show kind of what we were gonna do and if it was gonna work. Then we had a critical design review where we met and presented with NASA, and they reviewed our design and gave us feedback. Prior to the flight, we had a flight readiness review. That was kind of the final report and presentation before the actual competition. And then during launch week, we had the launch readiness review where the rocket was audited and every part of it was gone over. And then that gets us to now where we're Capstone presentation. We have one more report to do, which is our post-launch assessment, and that'll be due May 1st. One big thing that NASA had us do before we even really kicked off the project, we had to create a work breakdown structure, so we had to break down exactly what we were gonna do and what each part of the project was gonna consist of. The work breakdown structure breaks that down into different levels. As you can see up here, the level 1 is obviously the NASA student launch competition. From there, we broke it down into 5 subsystems for our level 2, the technical design of the rocket, our project management aspect, our payload, the STEM engagement, and our safety. During this presentation, we're mostly gonna be talking about the design of the rocket and the payload. From there, I'm gonna let Antonio come talk to you about the launch vehicle and everything that makes it up.
Before we could actually begin working on the rocket, we kind of needed to understand what happens throughout the flight. As you can see through this image right here, we first load up the rocket on the launch pad and we launch it from there. From there, we ascend and we reach our apogee. Apogee is basically the maximum altitude that the rocket was able to reach. From there, we have our first separation, consisting of the drogue parachute, which is the smaller parachute kind of made to reduce the velocity upon descent and also make sure that we don't drift too far off. If we release an 84-inch parachute, we will be drifting off a little too far. From there, we get to our main parachute deployment and finally the recovery of the rocket. Kind of having that set in stone, we needed to understand what we wanted for the rocket. For our purposes, we knew we needed to have the drogue and main parachute, 2 forms of separation, and kind of more like 3 points of separation. We also knew that we wanted to have our charges on 1 coupler, and when I mean coupler is this little tube right here. This is a coupler that basically connects both body tubes together so they're stable throughout the flight. And finally, we knew that we must be able to deploy some kind of payload from our rocket. Having those requirements, we needed to kind of figure out the configuration of our rocket. From here, we decided to just draw up a bunch of different ideas and we would pick whichever one seemed the most appealing. Configuration number 1 and 2 all go through the whole flight. So we start off at the launch configuration through the drogue deployment, our main parachute deployment, and our recovery. One little point I would like to mention is this circle right square right here with the 2 extra squares indicate our charges, where our charges will be presented. So going over this a little bit, we have our configuration number 1 with our drogue parachute being deployed, followed by the main parachute being deployed, and finally our camera system. For this configuration, we decided to kind of have the camera roll up from the middle of the upper body tube. For configuration number 2 is slightly different. We have the main parachute in the front with the drogue in the middle and our payload in the rear. Key difference between these 2 is obviously the payload gets pushed out from the bottom body tube. Our third configuration is similar to the first one. The main difference is the payload gets pushed out of the nose cone. Moving on to configuration number 4, it's main parachute in the upper body tube, payload in the middle body tube, and finally the drogue in the lower body tube. Now, one point that we would like to make here is the charges are on 2 different ends of the rocket. We didn't want to do that because there could be some problems that occur, and we wanted a reliable rocket. For this reason, and we decided to go with configuration number 3. It just seemed the most appealing, and also it's typically what you see when building rockets. having the configuration, we needed a form of way to simulate our anticipated rocket. So RockSim and OpenRocket are both two softwares that help calculate trajectory, meaning we are able to get altitude, rail exit velocity, actual full velocity of the rocket and such, based off of our masses and other variables. This software does not take into consideration any form of aerodynamic analysis or finite element analysis. This is just strictly for trajectory, I guess you could say. I'd like to point out that this was our initial rocket that we had designed, and you'll be seeing that it kind of changes a little bit throughout the presentation. So with both of those simulations, we were able to kind of get some basic results. As you can see for RockSim, we have an altitude of 5,100 feet, which is what we decided to have as our target altitude for competition. We have a maximum velocity of 411 miles per hour, our descent time at 73 seconds, and finally a maximum drift distance of 1,477 feet. As you can see, OpenRocket gives very different results. Further down the line, we kind of figured out that this was because OpenRocket and RockSim take into consideration the drag coefficient very differently. RockSim has a very low drag coefficient, while OpenRocket is very high, and we didn't really notice that initially. Here is kind of how we organized the rocket. We decided to have the payload in the front, with the linear actuator more towards the back of the middle, of the upper body tube, sorry. We have our GPS and a coupler that's right in between the upper and the middle body tube. We have an 84-inch main parachute with its respective shock cord. We have all of our electronics in the coupler between the middle and the lower body tube. And finally, we have our drogue parachute with its respective shock cord. All in all, we were able to kind of get a height of 102.7 inches, which is just above 8.5 feet. We have an outer body tube diameter of 5.15 inches, and finally, estimated weight of 24 pounds. For the material, we decided to go with G12 fiberglass, and for the fins, we actually constructed those out of aircraft plywood. We decided to go with the G12 fiberglass mostly because it was superior to our other alternatives. We decided to initially look at paper body tubes. They're more heavier than the fiberglass. We also looked at carbon fiber, and carbon fiber is very nice, but it's also very expensive. For that reason, we decided on the G12 fiberglass. Now, the plywood for the fins just seemed a lot more easier to work with than actual fiberglass. We could put it on the engraver, the plasma cutter, laser cutter, or the router, and we would be able to get the shape of the fins that we decided. Having all that, we decided to go with the Aerotech K1050 for our motor. Now, we picked this motor because it has the impulse to get us to the altitude that we're looking for, as well as the average thrust to help us get off of the launch rail at a steady velocity and kind of give us a stable flight. Piggybacking off of the stable flight, for this rocket initially, we had discovered that our static stability margin, which is basically a unitless value that describes how stable the rocket will be during the launch. For us, NASA preferred that we keep it between the 2 and the 2.5, and 2.36 is kind of what we got based off of our center of pressure, which is located on the upper portion of the lower body tube. And this point is just where the majority, all of the aerodynamic forces will most drastically affect the rocket. The center of gravity is 59 inches from the tip of the nose cone, as well as the body tube diameter 5.15. And this is kind of the formula that we had to use to get to that static stability margin. Also, the software gives us this value. OpenRocket kind of provides very similar results. They're just slightly different. As you can see, the center of pressure is just a little off, and the center of gravity is a little off. But overall, they're very close. Now I'd like to pass it over to Chad for our recovery.
So our recovery system consists of 2 altimeters to begin with. The first was an egg timer altimeter, which interfaces well, and it has a phone web browser ability, so we were able to test our ejection charges with that, and without a complicated vacuum chamber system or something like that. And then our second altimeter is a lot simpler, but it served as a backup because it doesn't use as much battery and lasts a lot longer. But both altimeters have to be capable of collecting flight data so that we're able to graph at the end of the flight. And they both deploy the main and drogue parachutes. One acts as a backup, so we have two different charges per parachute, and each connects separately. Moving on to the parachutes, the next key component of our recovery system. The parachute we used was an 84-inch ultra-light fruity chute, and this allows us to compactly, or ultralight, use a lot less weight, and then the drag coefficient of 2.2 compared to a regular parachute of 0.75 to 1.5 coefficient of drag. This means that our parachute can be smaller and it's lighter, so less space in the body tube and less heavy rocket overall. And then our drogue parachute is a 12-inch parachute, and this one doesn't really matter, but it happened that our subscale used a 12-inch drogue as well, and we just needed to slow down, like Antonio said, just slow down enough during the flight so that when the main comes out, it's not a drastic impact and we have a safe force there. And then the retention between parachutes, between body tubes, and the motor tube casing is a 5/8-inch shock cord made of nylon. And we chose nylon because it needs to be elastic a little so that when the main parachute deploys, it doesn't just snap. Our other option was Kevlar, which is not quite as elastic, and it doesn't store as neatly. The nylon stores very nicely. We just kind of like fold it over itself, and it packs into the tube very well. And then the stainless steel quick links, they just need to be as strong as the cord, and these are only added to provide quick disassembly and reassembly, so that if we need to take it back apart to fix something, or if the altimeter comes loose, whatever, we can just take it apart quickly and put it back together. And then the GPS we used is a featherweight GPS. This can record data all the way up to 164,000 feet, and it samples 10 times per second. And this is a lot better. Originally, we had a GPS that sampled every like 5 minutes, which is not good because the flight is only 1.5 minutes. So if it doesn't sample the whole flight, we're not going to know anywhere the rocket is if it does come down and it blow up or whatever. And it's very light. That's a very tiny little device. Within the rocket, it's only 15 grams. And I'm going to hand it off to Patrick for the payload.
So now that we've discussed the rocket a little bit, we can start looking at our payload design. How this is going to work is I will first discuss the requirements, including some of the objectives and our constraints. Then Zach will discuss the subsystems and look at our analysis and alternatives and how we did our final selections. And finally, I will then show the payload design, including our final diagrams and our planned sequence of events. So our mission objectives primarily is to use a camera to view the surrounding landscape of the launch site. To do this, we need to receive APRS transmissions that NASA sends. APRS, what that is it's just automatic packet reporting system. So essentially what that means is it's a method of sending information using radio waves. So NASA sends those radio waves out, and we need to be able to interpret those and then have our payload act accordingly. To do that, our camera needs to take timestamp photos. It needs to be able to rotate 360 degrees to view the entire site. And it needs a field of view between 100 and 180 degrees. At the bottom right, you see some of the possible commands NASA could have sent. You see they could have turned the camera 60 degrees either direction. C3 is take a picture. We could have had color change from grayscale and back. We could have rotated the image. So essentially, NASA sends a code that says A1, B2, C3. We must follow those commands in order with our payload system. Some constraints of the payload is that it had to fit within 24 inches of the rocket tube. It had to weigh under 2.5 pounds, and it could not be jettisoned away from the main rocket, meaning it can't float away by itself. It must always be physically attached somehow. while designing the payload, we had to consider the situation of the field. To start, our rocket and payload had to land within 2.5 feet of the initial launch site. Furthermore, more importantly, on the right side, you see the expected field conditions on launch day. You may notice there are troughs and there's dead grass, and we had to consider that while designing our final payload. I'll now give it to Zach to talk about our payload component selection.
So the first thing we had to do when selecting components, there's an endless amount of combinations that we could have went through to decide what we wanted to end up doing. So we decided to do a table format. We gave numerical scores 1 through 3, 3 being it met all of our criteria, 1 being it didn't meet any of the criteria, and then the scores were total and the selection was made. You will notice though, sometimes the highest scores were not selected because there was some attributes from other selections that kind of weighed over into the other ones. So the first thing we needed to do, we needed to figure out if we were going to have the payload come out of the rocket during the flight being attached with the shock cords, or if we wanted to deploy it on the ground. We didn't really like the air option. We felt like there was a lot of forces that could affect the payload when it landed if it was detached, so we'd rather have it be safely stored within the body tube. So we ended up selecting the ground for the ejection method. From there, we had to decide how we wanted to get the payload out of the rocket. So we decided between a push design and a burst panel design. From the beginning, the team decided we wanted to have the most passive system we could to eliminate any points of failure. So that is the main reason we went with the push design over the burst panel design. We felt there was a lot of point of failures with these doors opening or malfunctioning, or having to figure out how it landed. If it landed the wrong way, the doors wouldn't be able to open. So that it goes back to having the payload safely stored within the rocket for the whole flight. From there, we needed a computer to control the payload system. It wasn't really an Arduino versus Raspberry Pi, it was a microcontroller or a microprocessor. For what we needed to do with the radio frequencies, we really needed a microprocessor for the higher capability. This is a point that I mentioned earlier. You will notice the Raspberry Pi scored less than Arduino. That happened because not a lot of us have experience coding the Raspberry Pi, so we wanted to stay away from that. We ended up recruiting some computer science people to help us code the Raspberry Pi, so that was really convenient in the long run. The next was the radio frequency communication system. So you'll notice we have a Bofang and a Raspberry Pi in every single one of these sequences. The real challenge is decoding the software. So within here, you'll notice there isn't a lot of space. So that was the main reason why we did not go with the TNC. The terminal node controller is a large box that is used to decode the radio frequencies. We just did not have the space to add that into our system. We also talked about making our own decoding system. With the timeline of the NASA competition, there was no way we were going to have time to figure out how to create our own decoding system. Ultimately, we went with the Direwolf software, which is a software that is downloaded on the Raspberry Pi, which gives the Raspberry Pi the ability to decode the radio frequencies. Okay, and the next thing is how are we going to get the payload out of the rocket once it's landed? We explored 2 different options, the linear actuator, and then we also, during the time we were in our mechanisms class, and we were talking about slider mechanisms, we felt this was a really efficient way to do it. There just wasn't, it all goes back to space. There wasn't enough space to operate the slider mechanism, as well as the radius of the disk would have had to been way too big for the inside of the rocket. We ended up going with the linear actuator. These were readily available. We were able to order it. We found one in the length that we needed in order to get our camera system to push all the way out of the rocket. This acted as part of our retention system to make sure the payload did not come out during flight. So overall, the linear actuator was safer, more practical, and more reliable. As far as batteries goes, between LiPo and lithium ion, the LiPo batteries were the safer option. They carried more power with a smaller battery size, and they were significantly more reliable. The camera system, this goes back to the Arduino versus Raspberry Pi. The camera systems that were available for the Arduino were not complex enough. Some of them wouldn't, they didn't have a high enough field of view. We couldn't put filters into some of them. So that differentiated between the 160-degree field of view camera or the 130-degree field of view camera. So ultimately, the Raspberry Pi microprocessor was selected, so the 160-degree field of view camera had to be selected, and it had a lot more capabilities. Everything in our payload was 3D printed, so we had to select a material that we were going to use to 3D print. We ended up going with PLA. We all had experience printing PLA. PLA was readily available at the school, and we knew we weren't going to have any issues, especially with the time constraints that we had. So we went ahead and went with PLA. Initially, we wanted to use filled nylon. None of us had ever used the resin printers before, and we didn't want to try to tackle that. It all goes back to timeline and what we could do in the short time span. The next thing was how are we going to get the camera out of the rocket? So we had to look at different options for lifting mechanisms. The first option we looked at was the screw telescopic method, which basically it's essentially left-hand and right-hand threads. As the motor spins, the left-hand threads will turn, which will turn the right-hand thread, and it'll push out. As far as space requirements go, we'd have to have a pretty large amount to push the distance that we needed. So that was kind of looked away. And the motor that would be required to turn that, we didn't really want to take on that extra weight. The next was the telescopic pulley method. This was very complicated. We were trying to reduce the points of failure, so we really didn't consider this option that heavily. It was really neat. If we could get it to work, it would have been really, really cool. But like I said, the time constraints, and we wanted to have a working functional payload at the launch, so we didn't end up going with that. The scissor lift method, that was our team's favorite. We felt we could understand that, it was doable. So everything was 3D printed with the scissor lift, and that moves us into the motor to lift the scissor lift. So we had to look at a lot of different gear ratios because we didn't want it to take too long to open, but we also wanted the motor to have enough torque to get the camera system out of the payload. This motor is tiny. It's ½ an inch by ¼ of an inch. It's extremely small. It provided enough torque and speed to get the camera system out of the rocket without having any additional weight to the payload system. And the most important part of our payload, I would say, is our latching relay. A lot of teams in the competitions did not do this, and with the times on the launch pad, a lot of payload systems died. So how the latching system works is we ran a third altimeter in our payload section that when on descent, the altimeter would send a signal to the latching relay, which would latch and power on our payload system. From there, our payload sequence could begin. We had timed for it to hold 3 minutes before it would activate in order to give it time to get to the ground, and then our system would work. Really, this was a game changer for us because it allowed us to not have to worry about conserving power so much. I'll now turn it over to Patrick to talk a little bit about the payload.
So for our payload final design, at the top you see the initial position of it. This is the position the payload is in prior to flight and during flight. At the bottom is the final position. This is the position of the payload after all the mission objectives have been completed and the camera has taken all the images. So the general system diagram can be looked at with the payload in the final position. On the left, we have the rocket GPS, which does not affect the payload at all. We have the altimeter with that, with a latching relay mounted right there. Moving along, we have a linear actuator, which is shown fully extended with these components called sled locks. Sled locks are needed because they prevent the sled from rotating during flight. The sled can rotate because it is mounted between bearings on either side. On the sled, we also have most of our electrical components, including our Raspberry Pi and our battery. We have our raising mechanism that raises our camera gimbal above the rocket body. And further right, we have the radio receiver, which is how we actually can receive commands from NASA. Also, our final weight of the payload was 2.2 pounds, which is below the 2.5 requirement we had. To discuss the plan, or how the payload is meant to operate, we can look at the planned sequence of events. So to begin, the payload altimeter is armed on the launch pad by turning a screw switch. After this, the payload launches, it descends, and at 200 feet, our altimeter sends a pulse through the latching relay, which switches, powering the entire payload and turning on the Raspberry Pi, linear actuator, and servo motors. After that, the body tube lands onto the field, and you'll notice the orientation of the sled when it has landed. Right now, it's sideways with the raising mechanism facing the screen. However, it can land in any sort of orientation. Continuing on, the linear actuator begins pushing the sled forward, and it pushes the sled out of the sled box, which then the sled can rotate due to a low center of mass, and it is, once again, mounted between those bearings. The linear actuator continues to extend until a gap is formed between the nose cone and the body tube, and the camera gimbal begins to straighten up using data from an accelerometer. An accelerometer is a sensor that can detect its angle relative to the ground, and is the only reason the camera can find its position and straighten. After that, a DC motor spins a screw on the lifting mechanism, which then raises the camera gimbal above the rocket body tube, and from there the camera can then take photos and complete its objectives using the commands sent from NASA. A closer look at the sled really shows the bearings on either side inside each bulkhead. You see the Raspberry Pi on the left with our 1,000 milliamp hour battery, and our 1/4 inch diameter steel all-thread rod, which is creating good structural support for the entire sled. On the right side, you can see our DC motor that spins up close, and our camera gimbal, which is made up of two 180-degree servos, which means they can only move 180 degrees for tilting, our 360-degree servo, and our accelerometer mounted on the side of that. You see the links the raising mechanism is created out of, and you can also see the center of mass and the axis of rotation, which helps illustrate how the payload, or how the sled can rotate through that low center of mass. To ensure our camera can straighten, we have a camera block diagram. Of course, we want a desired camera movement. So waiting for information from our decoded radio frequency signals into our Raspberry Pi, which then moves our servos, which then moves our 3-axis camera mount, and eventually creates a camera movement that straightens our camera. This is our closed feedback loop. I'll now give it to Antonio to discuss more about the radio frequency system.
So as Patrick had stated, we needed to use an APRS system, which is the automatic packet reporting system. All of this is a system that takes information, written data, encodes it into a form of sound for our radio to pick up and later be decoded through our software. So this is something that works on anything Linux, Windows, Raspberry Pi, and when we heard Raspberry Pi, we knew that we needed to figure out how to incorporate this into our design. As you can see, we have the Baofeng, this radio that's sitting on the table. Yes, we actually put a radio in the rocket. This radio was able to send that data to a Raspberry Pi that was decoded using the Direwolf software. It's just a software that is able to interpret all that sound and decode it into what we needed to. From there, it just gets converted into something that the microprocessor can read. Kind of going over the whole system, we have the radio frequencies that get captured by our antenna, our radio basically. That gets sent to the Direwolf software on the Raspberry Pi. From there, that decoded frequency gets sent to the camera system, which then sends it to the servo to kind of rotate to take the pictures and everything. And finally, we get the pictures to be taken. Now I'd like to pass it over to Chad to talk about the subscale.
So during the subscale launch, we didn't have a payload or anything in there. We did add some simulated weight in order to have the rocket act the same way as the full scale would. And we launched it twice. We had altitude of 619 feet and 1,200 feet. And both times it was a drift distance of less than 500 feet. On the subscale, you see the fins there. The first launch was with the fins, the second was without. The first launch also had a smaller motor, hence the big difference in altitude. That wasn't a flaw or anything in the flight. Some requirements of the subscale are max scaling of 75% and must closely resemble the main rocket, hence the fins. That was the original design. And then must use a motor above an E-class and below an H-class. And then some test flight goals during the subscale, during both flights. is to verify our checklist and make sure that we weren't missing anything, make sure we didn't have any errors. Verify the simulation through RockSim and OpenRocket, and then test dual deployment system. None of us have launched a rocket before, so we needed to figure out how that worked. And then practice rocket manufacturing skills. There was a difference between, this subscale was made out of cardboard just for simplicity and not wanting to spend a whole lot of money on the subscale, but it acts the same way as the main rocket launch. And then post-launch rocket placement, make sure we take plenty of pictures. NASA was hard on us on that. Make sure you take a lot of pictures after the flight. And then during the first flight, the egg timer was the only altimeter to capture data. We predicted 762 feet, so there's a bit of an error there. And then some of the flight results that we did, we updated the checklist based on some things we found, double check altimeters, and add a first aid kit to the checklist. And we implemented dual deployment system, and it worked fine, it was great. And then we also experienced our first failed altimeter during flight. No big deal, that's why we had 2 altimeters, but we had to check and figure out why that altimeter failed during the flight. And then our second flight was much higher. We had a predicted altitude of 1,482 feet, and each altimeter read slightly different results, but within 100 feet. And then for this flight, we also updated the checklist, checking E-match connections. We had one charge that didn't fire, but the altimeters worked. It was just a connection to E-match itself. And then we prioritized data collection on this launch. We took loads of pictures and did lots of analysis. Moving on to full scale, Antonio's gonna talk to Tom.
All right, so we had a total of 3 different launches, but we will only be discussing 2 because though the second one was mostly incorporating the structure of the payload. Anyway, the first test flight that we conducted was reached an altitude of 3,950 feet and only drifted about 1,300 feet with winds at 12 miles per hour. As you can see from the simulation, there's a bit of a difference. The total length of the rocket increased to 103.6 inches, and the final weight of the entire rocket, including the motor, ended up being 26.6 pounds. Kind of our goals for this flight was just to verify our pre and post launch flight, kind of to check and our checklist and make sure that everything that we needed was incorporated into that. Kind of verify the errors in our simulations, which I'll talk about in a second. And again, test the dual deployment, make sure that everything is functioning properly, and make sure that the rocket is able to be recovered in a safe manner where nothing is broken and everything is able to be re-flown. These are the altitude results that we got. We have a maximum altitude of 3,948 feet using the egg timer altimeter, and also altitude of 3,969 feet. As you can see, there's a very large discrepancy between our simulated and actual, but I'll get to that in just a second. One thing that we noticed was that the nose cone hit a little too hard, but that was because we added about 1.8 pounds of mass to the front of the nose cone to kind of help us get that stability that we were looking for. Our booster section acted as an anchor, and also our payload failed to activate, but that was also because we didn't have the fully built payload in our rocket. Kind of going over the results a little bit, we have the center of gravity at 60.1 inches from the tip of the nose cone, our center of pressure at 71.35. That value will not change. And our static stability margin of 2.19, as you can see, it's a little bit lower than what we had originally simulated, but it's still a valid number. We were able to get our entire flight in just under 100 seconds, 97 seconds, with a descent time of 85.93 seconds. Using both altimeters, we were able to get an average altitude of 3,958 feet. Here's just the kind of the pictures that we were able to capture from this launch. The anchor acted as, the booster section acted as an anchor. The parachute was actually able to drag it a couple feet before it was secured. The nose cone was able to hit the ground a little too hard, but that's okay. And as you can see here, everything lined up very nicely. There was no tangles, everything. It was a very nice recovery. So this probably should have been done earlier. However, we managed to figure out how to get our altitude to match with our simulations. And that was simply by adjusting the drag coefficient. So our original drag coefficient using RockSim was 0.33. That's a very low number. That's why we were able to get simulated altitude of over 5,000 feet. Upon updating this value through just messing around with the simulation, kind of just adjusting it and seeing how close we could get to it, we were able to get a value of 0.7. And this number right here was able to get us to more accurately define our altitudes with our simulations. For the final launch, we were able to reach an altitude of 4,143 feet, which is an improvement to our original. This was done through adjusting the masses, moving stuff more forward, and kind of getting rid of stuff that we don't really need. This rocket only drifted 645 feet at 8 miles per hour, which is less than what we had originally tested with. And as you can see, it just got 0.1 pounds a little bit more heavier, but we still managed to get the higher altitude. Our perfect flight altimeter was able to record the value of 4,143 feet. However, our egg timer died on us. This was due to NASA's end. They had us on the launch pad for over 3 hours. We had originally designed this system to work for a maximum of 2 hours. When we checked it, it was working. In that little bit of time, it was enough for the system to just die. But overall, we were able to get our first activation of the payload upon landing. So just to summarize some of the results that we got, we moved down our stability margin, which is why we were able to just get a slightly higher altitude. We were able to get our total flight time in 92 seconds with our descent time in 74.6 seconds, which is a bigger improvement. And using the MissileWorks altimeter, which is the one that is attached to the payload, we were also able to kind of verify our altitude to be 4,145 feet. Okay, so based off of our first launch, this one is slightly different. This didn't land as nicely. As you can see, there's a big knot right there. That happened during the deployment of our parachutes and everything. Not really sure how, but it happened. And as you can see right there, the camera is peeking out, saying hi, taking pictures after the fact. But yeah, also we would like to point out right here, our parachute got tangled, which was a blessing, because if a little bit of wind would have come up, it would have opened up the parachute and could have dragged the rocket a little bit more. And as you can see, the ground is just a little bit harder, so it would have been more difficult for our booster section to act as an anchor. Going on to the payload results. Our latching system worked perfectly at 300 feet. It deployed, powered on our Raspberry Pi, which then allowed for the linear actuator to push out the camera system from the tip of the nose cone. Our DC motor was able to raise the camera system. The accelerometer did not function. It was disconnected sometime throughout the flight, and we were only able to figure this out after going into the Raspberry Pi and checking the log to see how the script responded to it. And there was, it stated that the accelerometer was disconnected. Direwolf worked. It was able to receive the frequency and the commands, but there was a problem having the Direwolf send the script to the payload handler. That was a coding error on our end. Also, the hard code was actually what took the pictures. NASA was nice enough to give us a script that we could encode into our system to, if something fails, this would take over and take those images. Now, even the hard code, it was missing 3 commands. This was also due to a small programming error. However, with all those, we were able to get pictures. So this is kind of the pictures that we were able to get. As you can see right here, we have a beautiful picture of the Alabama sky. This one's a little bit more difficult to see, but this is a saturation filter that was applied to it, but still of the sky, and we were able to get the camera to rotate 60 degrees and get this really nice picture of the ground with a very small horizon up on top. So we were very excited for these results. And it's just a small little video of our launch.
Pad number 10, we have Rams and Rockets. This is Angelo State. So this thing, the rocket is Candy Ram. It's 26.7 pounds, 5.15 inch diameter, 8.63 feet tall, Candy Cane inspired. It's got CADS, which is an acronym for the team members' names. It's flying on a let's see, the Aerotech King 1050. It should go 5,100 feet. On pad number 10, we have a clear sky. We have a clear range. We're gonna go in 5, 4, 3, 2, 1, ignition. Let's go. First. All right, one more. Oh, where's you at? Oh, where you at? Right there. It's probably a couple thousand feet up. There it is. Here it comes. He's coming down. Okay, we're about 1,000 feet up before the main comes out. You're over there. There you go. And then they also did 3D paint or 3D print the inside parts to also match the school colors. So the original team was 4 members. The team worked from scratch and they had no history to work from. So pretty remarkable they got that all together as a team.
And Chad will summarize our cost analysis.
So at the beginning, we budgeted 5,000, and we were actually able to raise more than what we budgeted, but due to the travel cost and having to buy so many motors, we ended up losing a little bit of money there. But it's $1,000. And then conclusion and acknowledgements. Overall, there was quite a few challenges with this. The NASA timeline with the Capstone timeline, it was just hard. We had to submit a report for NASA, submit a report for Capstone, and build. We were able to build off of each of those, but they were separate reports. And then APRS system, I don't know if y'all heard at the beginning of the presentation when it went like, that's APRS. So dealing with that was a challenge. It's just a random sound and it outputs letters and numbers. And then the initial rocket knowledge, none of us had any experience with rockets, dual deployment, parachutes, any of that. So like the video said, we were learning pretty much from scratch. And then the payload presented challenges all of its own. From getting it to balance right, get everything to stabilize, and then at the launch, you can see in the pictures, everything was stable, and just that final, last little wire just needed to happen on the accelerometer, and it would have worked perfect. But anyway, little bugs like that were constant. Team dynamics, we had an excellent group. NASA at one of the social events actually asked everybody oh, did y'all have great team dynamics? And everybody said no. And we looked at each other like, are ours was amazing. So 4 of us, it was a great group. And the rocket community as a whole, along with the radio community, everyone's just so supportive in these, I guess, hobbies. They're just so supportive. Like, we came in with nothing, we were able to build a rocket in a year. Like that, I think that's incredible. We were able to use a lot of knowledge from everybody. And then future improvements we would make, if a group did it next year, create milestones for the payload. Because NASA is only worried about the rocket safety. They want to make sure you meet a bunch of different milestones throughout the process, but they don't really make you like, oh, have this part of the payload functioning by this time or anything like that. So having separate milestones would be really beneficial, and maybe we could have ironed out those kinks of the payload a lot sooner. And then we wanted to give a special thanks to all these people on this list. From the STEM engagement that we spoke about, we didn't have to touch that. We just handed it off to some people and they took care of it. Programming, we were not going to be able to program the Pi in the time it was required. And then, like I said, the rocket mentor and then the radio club helped us as well.
Time for question.
That's your hand come up first.
Okay, so by the way, great project, really proud of y'all. Yeah, so about the timer, on the egg jumper that you mentioned, that it wasn't able to work.
The altimeter, the egg timer, yes.
Yeah, so do you think that could have been like fixed for it to last longer, or were y'all aware that it was gonna be like an all-day event that you might have to like prepare for longer hours?
NASA said that we were, we should account for sitting on the launch pad for 2 hours only. And they had us sit out on the launch pad for 3 and then some. So we had tested it, we had done the calculations. It was gonna work for 2 hours, but just that that extra hour is just too much for it.
Will you feel for next year it would be best to prepare for like 4 hours or a longer period, or do you think the 3-hour window should be enough?
They did start pulling rockets off of the pad after 2 hours. Just for us, we were confident, a little too overconfident. But like the Stratologger, that one worked perfectly. That one could still go on a little bit longer. It just, I would do your analysis on the battery and see fit for you guys.
Yeah, I'm just taking mental notes here, because I know I want to do it next year, so. And what else was it? Oh yeah, how, like overall, how did y'all place on in comparison to everyone else, y'all know?
We won't know until June 6th.
Until June 6th? Damn, that's my anniversary, great.
So you made a recommendation for payload, right? So other group should create some milestones for the payload. So if another group decides to do the same capstone presentation and attend the competition next year or a couple years from now, would they use the same rocket that you built, or they need to do it from scratch?
This all starts over from scratch. And so like last year, the payload was a lot different. They had to do a drone. This year it was this system, but next year it could be something different. But NASA prefers for the rocket that it's done from scratch.
Well, it's actually a requirement for the.
A requirement that it must be started from scratch.
Because they mentioned that there is no history for San Angelo or Angelo State University, so that's why I was curious about.
They'll be able to take our simulation data and some other things though to fix the errors that we made early on. So
Okay,
they
that
have
was
data
my
to build
second
off of
question.
now.
Yeah,
Yes.
okay, they will monitor that if there's any improvement or over the years, right?
Yes.
Okay, good.
So you mentioned you had to change the drag coefficient. What made you choose the original value?
That was based off of the simulation. Like we didn't touch that value. That was set by the simulation. But we were told to adjust it. Kind of overlooked that a little bit too much until it was too late. But after adjusting that, we were able to get the altitude to kind of match with our simulations.
So you practiced flights in Texas, but then your real flight was in Arkansas. How did you prepare for like the different kind of weather conditions and whatnot that would be from state to state?
So the weather was good. That's
What were the conditions that would have made a difference, and why did you decide that wasn't important, or did you just not do it? Did you actually look at it?
Initially, we did, but at the end, it was something that we overlooked completely. Just,
So off the top of your head, what conditions would be, I mean, what would change the
Humidity.
performance of the rocket? Huh?
Humidity would have been the big thing, like
Right.
the charge wells would have got wet or moist.
Air density and, I mean, air density is the main one, right? So,
You said you were talking about the flight simulators?
Yes, ma'am.
So is that something that you program? I'm not familiar with what that is. Is that just something that you program that tells it what to do or what? Is that like a standard thing you buy and then you can program into it, or what does that do?
So that basically, we designed the rocket to how we believe it's going to be, need to be made.
Right.
We input the material, so the plywood, the fiberglass, all of the components, the motors and everything, and from there, this simulation is able to calculate our altitudes, our velocities, and other variables.
I'm talking about the electronics, the things you're referring to is more.
Oh, the altimeters.
Oh, was it the altimeters, or I'm sorry, that those are used in there to do what? To tell it what?
Oh, those?
Yeah, that's, I'm sorry, maybe didn't say, yeah.
Okay, yeah, those, in the simulation, you just plug in the altitude that you wish to deploy those parachutes at, or how late you want it to deploy the parachutes. So you just input those values and it'll simulate it for you. Now, when we actually go to program this, we have to take those values and program it onto those.
Okay, very good. And why did they ask you to put it why did you put first aid kit in? Why did you put a first aid kit in?
Somebody cut themselves.
Who and how? Like when it landed or?
It was on, it was during assembly. We had to splice some wires, and the safety officer was not being very smart.
And so y'all opted to put.
Yeah.
Cute.
So we included first aid.
Safety first, right? Okay.
So I did have a follow-up question on the drag coefficient and the modeling. Did you guys just play around with those numbers to get it to simulate what you guys' flight was? Or did you guys actually run an actual drag coefficient equations to figure out the best method for that?
It was actually a bit of both.
Okay.
CJ was able to write a script using Python to kind of get us an estimate for that drag coefficient, and also messing around in the simulation to get us that value. CJ got a value of 0.75, and I got a value of 0.7. So those were very, very close to each other.
And then another question, on the retention straps, how many uses do you guys anticipate that your retention straps will be able to hold before it fails?
At least 4.
At the moment, these are very cinched up. They're very burnt and everything, so we only got.
In the checklist, we go through each of them and make sure they're not frayed or burnt or. And we looked at it after, and it's good for at least one more because the cords seem fine. They still have elasticity in them, and so I wouldn't put a number on it. I would just check it. Or I would rather.
Okay, so y'all mentioned some of the issues whenever you launch the rocket. Do you think, and you only figured out until you launched it, do you think they could have figured out those issues after you had more launches to do more testing? Do you think, we could have had more testing?
I know for sure the drag coefficient one could have been figured out during the subscale flight. So that's essentially kind of what the subscale flight is for, to kind of just help you adjust those values and variables to get you that results that you're looking for. But I overlooked that.
And I'm just curious, if it's something that could be printed books, because for instance, whenever y'all mentioned that that y'all got, that the parachute got entangled, it's like, okay, that sounds like a matter of chance, so how can we prevent the next time so it's not a matter of chance and that the rocket lands safely on the ground? Because, if that had not happened.
Yes. So, I think that also goes into talking with your mentor. Your mentor will be able to know kind of, I wouldn't say standard ways, but the most optimal ways to pack your parachutes in order to get it to where it doesn't tangle up upon like the deployment or anything.
And we explored options through that, just the timeline. If you can reef we were talking about options to reef the chute to where, you know, it wouldn't tangle and it would pull it in, or it wouldn't open up and drag the whole rocket system. Just, everything's gonna fall back on y'all's timeline when y'all do it again. You just gotta make sure you plan for enough time.
And we really think that the reason that it tangled in the first place was because the backup charges were used, which are much more than the main charges. So you'll hit the end of the shock cord and then some if it would have like fired on the main, but the main just didn't fire. So like, if that makes sense. Like, it hit, snapped together, and then tangled, and then the parachute's out. If the main fired, it wouldn't have hit the end of the shock cord so violently.
It sounds like some of those issues derive from the batteries, like just draining, but that worked in Nell's labor.
One system fails, it'll lead to more failing.
So to piggyback on Stephanie's question and use some inside information. So when was the first time that the payload operated correctly? That you tested it and operated, you thought it was gonna operate, that it operated correctly as far as your pre-testing? When did that occur?
3 o'clock in the morning before.
Right. And I'm really not picking on you, but it's I think an important point. So my question is, kind of back to Stephanie's question about testing, how would you have changed the payload design and testing system or something? And I don't need a big, you know, how would you solve that problem? Because that was the real, and you were not the only team up till 3 o'clock in the morning the night before trying to get their payload to work, so.
There were some teams there still working.
Yeah, there was some working on the morning of the flight, yeah.
I think it all revolves around the milestones. If we would have set those milestones and had points to meet for the payload like we did with the launch vehicle, there wouldn't have been any issues. We would have made sure all that stuff was ironed out before that it got to that point.
Because there's a lot of testing you could have done without flying it for the payload, for instance, right?
Radio frequency stuff.
Yeah.
We could have done that long.
I know we had a lot of test plans, we had a long list, and we just couldn't make the schedule. Every time you would, you know, hit a schedule and you'd push it back, so.
Right.
Well, then we would break things as we were testing. So we'd move forward and then we'd go 3 steps back and we'd prepare something and then test again.
Yeah, I mean, you could easily run this as one design project for the vehicle and and a separate almost a separate design or a much bigger team if you were to do it in one project, because the payload, as you pointed out, NASA's the thing that I loved the process that NASA held you to in terms of the design process and requiring you to go through alternative designs and requiring you to define what your test goals objective are. That was great. They're focusing only on making sure that the rocket flies safely. That's why they're doing it. And they say, okay, you guys figure out your payload stuff. And that's why the payload is harder for a number of reasons. And actually, I think if NASA held you to the timeline, to the requirements on the payload that they did to the rocket, very few teams would have actually been able to fly because they wouldn't have met, because if they'd held you the same ones, you wouldn't have met those timelines, right?
We would have to have, like you said,
Yeah, and so I was actually pleased at that point that they weren't holding you to those as you were struggling through the end of it, because at least we're gonna go fly a rocket and it was gonna fly safely, so. And how many, how many total flights did you have on all your rockets?
5.
And how many catastrophic, non-functioning flights did you have?
0.
That's amazing.
That's pretty amazing.
Yep, way better than I do. So.
I saw you had a question, Andrew?
Yeah. So I was just curious, so with the Open Rocket and RockSim, with those 2 programs, so it sounded like y'all use those kind of in parallel throughout the project, right?
Yes.
And you were mentioning like in the beginning that the Open Rocket was like giving you more conservative like altitudes that it would reach because it had like a different like drag coefficient or way of calculating drag, right? So, and then later you mentioned too how y'all ended up finding out that the drag coefficient was a little too small. I guess for both programs, and then y'all raised it up to like 0.75, right? So which one ended up being like more realistic to what y'all actually got, like, when y'all launched the full scale model? Like, which one was closer between those two programs?
I'm gonna be honest, after we figured out the drag coefficient, we kind of started ignoring Open Rocket, just because we were also running on time constraints. We weren't having the time to be able to remodel the rocket, because that was a little bit of a problem. Once you imported the rocket, you had to fix it every time for some reason. And we just felt it was easier to just stick with RockSim. And once we figured out that it was able to get us those altitudes that we were looking for, we kind of just ignored it. Not good to say, but. Yes, ma'am.
I have a question. You mentioned that you had students from computer science helped out. How were those students recruited to help out? Were they compensated? Is it just because they wanted to help out?
All the students that joined us, they were here because they wanted to be here. It is a big project. It has a big label onto it. Just mentioning, hey, there's a project that we're working on. It's with NASA. Would you guys be interested to help? Majority of the time, they said yes.
You might reiterate what all the you did this early in the thing, but what are all the components of? Because you're talking about the rocket, but there were 3 other components to the competition, right?
Oh, the STEM engagement and is that what
Yeah, right. So what were you doing for STEM engagement, and what was that, and what were you doing? What your team? Right?
So they were events that basically reached out to the community and basically educated people on different science matters. We mainly focused ours on rocketry. There was other options to talk about Newton's laws and things like that. We revolved ours around rocketry. Vanessa did a really good job. We did a few lab nights with the school, and then they reached out to a few other elementary schools and things like that to meet that STEM engagement milestone. Stephanie, she did a really good job with fundraising. She reached out. She did 100% of the fundraising on her own. She raised quite a bit and got a lot of support from the community. Braxton and Isaac, we recruited them from the computer science. They did an amazing job. We wouldn't have got anywhere with the code without them. They were a huge help. Allie, she was our social media. She's getting a degree in communication. She helped a bunch. We had another requirement where we had to have social medias. We had to have TikToks, Instagrams, things like that. She actually made our social medias very popular. We're actually getting lots of likes on them by the end of everything. Brad helped with designing the eBay sled. That came in really nice. And then Ricardo helped with me with the scheduling and project management. Big thanks to Jim, our mentor. He was a huge help. A lot of the stuff we would have had questions on and had to find out on our own, we could go to him really quick, ask, and he'd have a real direct answer. And then the amateur radio club, we reached out to them. They were really helpful. They gave us all the equipment we needed to send our own signals. They had the amateur licenses to deal with the radio frequency, and it just all, the whole community came together, the community school to really complete the project.
I just don't see Dr. Kitch's name in
Dr. Kitch's a big help
because he's
too.
your advisor, I mean, without him, you wouldn't do that project.
Dr. Kitch is a really big help.
Yes. And then our weekly meetings so every week you met and then discussed, right? So,
Yes.
Huge help from Dr. Kitch.
Mm-hmm.
You just forgot to put his name.
I want to, at that note, I want to steal the show for 30 seconds and ask Jim to come up here. So Jim Ballard is the mentor for this. Technically, these students aren't allowed to fly this rocket because they're not certified to fly rockets this big. And so this program requires somebody that's certified as a high-powered rocketry flyer to do that. We have lots of people that help our students out. We have lots of folks in here that can help our students out, but very few of them will travel 4 days, take 4 days out of their time to travel all the way to Alabama to go on the flight. We'll be here at any time, donate hundreds of dollars worth of equipment, and loan us hundreds of dollars worth of hardware that we can use for this. So this is our department coin, Jim. And thank you very much for everything you did.
That was I had a great time.
I do think if you have any more questions, you can catch them during the break between this and the next session. We got about 6 minutes or so now. And so maybe we'll start about 2 minutes late on the civil presentation. And
there's snacks in the back.
And yeah, reminder, there's some snacks in the back. Go and grab them. Go ahead and talk to these guys. Good job.
Sorry, we really did not calculate the valid thing.
I forgot to ask them to get their, are they getting their licenses? Did you, I forgot to ask the question.
It's mechanical engineers, man.
Hey guys, come here. All of y'all. Mechanical engineer's license, your license, go take your fundamental exam, get your license. We are so short of mechanical engineers licenses.
I can't get the mechanical engineers to get their license, to do the FE exam.
Oh, great, y'all did a great job. So, get your license, go take your exam, get your plates. We are so short, and we need to do it right. Then you go do the same thing. Great job. And that was good.
What's up, Joseph? Answer call.
I'm just gonna get the word done. Drop my water. You would think so. You would think so. I'm ready. You
guys see the symbols? You are.
So I'll give you, whenever y'all find a chair. Are you staying too? So y'all are so over here in case you need to.
Yeah.
So it's the rising I missed it because I had no class. Oh, yeah, so
That is so interesting. Slip down. No, they said, I just gone into their meeting and said, I need one of you for your boy. What would have happened? We've been all over him, right?
Now they are good. Now they are good.
Y'all don't get it. I have 20 years of this, y'all know. So, yeah. But anyway, and they won't even listen because they're so. But it's okay. So I just, no, ma'am, I'm not, I don't, thank you. Okay. We got it. And that right It's so much.
Yes, sir.
Actually, no.
Why is everyone scared?
Oh, yeah. Oh, yeah.
You only have a 6. It's not a very true. Well, I did get that.
Yeah.
They're saying rainbow, okay.
Thank you.
Yeah, you should do this minute. You should run.
Hey, buddy. What are you doing? How are you? I think don't. Thank you. You're free. You're so broke.
She does that to you all the time. Yeah.
Yeah, that's Steve. Uh-huh.
I was about to call you, big Kelly. Hello.
All right, welcome everyone. It's a pleasure to have you, and as always, it's a pleasure to be the faculty advisor for this team. So we had a great semester together, many fun times, many fun nights, many somehow very many late night chats. I'm not sure I've had that many before. This group loved to work late at night, and so somehow I guess I do too. So it all worked out together, and so I'm really pleased to have them present their results for you. I'm very proud of them and the work they accomplished this semester, and look forward to seeing it and hearing some of your feedback, and hope you enjoy the presentation. I will pass it off to our team lead, Drew, to introduce the team.
Hello everybody, thank you for attending our 2023 Capstone presentation over our Foster Road improvement. My name is Drew Dykes, and I am the team lead for our team 10 out of 10 engineering. Just some background on our name choice. So we are the 10th graduating class of civil engineers from Angelo State University, as well as it's a testament to the quality of work that we produce, always 10 out of 10. None of this could have been possible without our amazing team members, everyone, including our senior design advisor, Dr. Anthony Battistini, works super hard and diligently throughout the semester. One more thing before we get into the presentation. On behalf of the team, we just wanted to give a big thanks to Mr. Russell Gully, our client, and his team over at SKG. They met with us several times over the course of the semester, and it was a privilege to get to work with a professional engineer during this project. And so with that, let's dive in. So our team's divided into 6 specialized engineering teams, each of which representing a key aspect of civil engineering. Each team member got to be the team lead of one of these specializations and got to take part as team members in multiple other teams as well. We did this to diversify our skill sets across the project, as well as to make sure that the work could be completed by the deadlines we had. So our project is located Foster Road, south in San Angelo, Texas. As you can see here, Foster Road is a 2-lane collector, and our limits on this side are from the north side of Buckskin Drive to the south side of the State Loop frontage road. Up there, just a couple things about our site. Foster Road is the only means of access to this residential area down here called Butler Farms. There are no other connecting roads to Foster Road, and you can tell this boundary right here is the South Contra River. So the purpose of this project is that in the master plan of the city of San Angelo, eventually Foster Road is going to be upgraded to where it runs all the way south and crosses that river so it's accessible from the north side from the loop as well as the south side. As far as our scope, our client requested that we design new plan profile alignments for Foster Road as an urban arterial street. Urban arterial is per the city of San Angelo spec, is a 64-foot width road. Our current one ranges from 20 to 24 feet in width, and so that just kind of shows the scale of the project and how much work is going to be involved. Our transportation team also had to design the type and placement of signs and pavement markers. Our hydro team had to evaluate the drainage conditions in order to propose a new hydraulic structure. We're going to be proposing a box culvert, and per the request of our senior design advisor, we're also going to be comparing this with a bridge proposal as well. Our geotech team performed the soil analysis in order to select material for our road and to perform the abutment design for the bridge. Our environmental team performed a stormwater pollution prevention plan and also set up environmental best management practices across the construction site. And our construction team is going to propose a probable construction cost as well as construction schedule. All right, so I want you all to imagine with me that you have been a long-term resident at the Butler Farms residential area. As you approach the road, as soon as your tires meet that pavement, you think, wow, this is a really smooth road. That's because of our geotech team's perfect base material selection, as well as our transportation team's immaculate pavement design. You also think to yourself, sidewalks? I thought we lived in San Angelo. You keep driving down the road, another thought occurs to you, there was a massive storm last night, but there's no flooding over my road. Well, that's because the hydrology team designed a perfect culvert to convey all the flow underneath the road. Now I want you to look into the future. As this road develops, you're going to be driving down the road with lots of other vehicles. You look out past the road, you see businesses, other residential areas springing to life, and none of this could have been possible without 10 out of 10 Engineering's Foster Road Improvement Design. And with that, I'll hand it over to the environmental team.
Hello, my name is Emma Seals. I'm the environmental lead, and with the help of Lorenzo, this is our environmental.
So just for our general scope, the main things we focused on was determining what permits were required, creating a SWIP report, as well as following all local, state, and federal regulations. So this is just a breakdown of the different regulations we're trying to follow. So at local, you have COSA, for Texas, you have TCEQ as well as TPDS, and then federal, you have EPA. Just so for the permit requirements, for TCEQ, we need a general construction permit. And then for EPA, we need a stormwater permit. And then for a construction site notice, for City of San Angelo. For our SWIP report, it's also known as the erosion control plan. It pretty much just details your pollution prevention, potential pollutions, and your BMPs. And it's required by both EPA and TCEQ.
Okay, so when we first started our project, we created a preliminary decision matrix. This was just so the original ideas we had, we could weigh and see if it would be a good idea for our project. For this one, for environmental, we listed our best management practices. So best management practices are structures or processes used to control sediment and erosion in the area, to control pollutants. As you see, we had some highlighted ones such as diversion ditch, outlet traps, and temporary seating, and these were measured by multiple values like cost, longevity, and construction speed. However, when we got further into the project, some of these just wasn't feasible, and just for temporary other reasons, such as diversion ditch, we felt like we could not just build an effective one for the site we had, or such as temporary seating. It could be difficult depending on the environment that we have. We need that to hold down a lot of sediment, and it could be difficult for that to grow. So on our next slide, we will be describing the best management practices that we did decide on using. One was being silt fencing. This is a temporary control device for sediment. This is good for serving as a barrier to contain sediment that is within the site and is not going to be outside affecting native soil that may be in the area. And this serves as a good barrier for in between work zone and native areas. Another one was a stabilized construction exit. This is one that's actually required for construction sites, and all vehicles, construction vehicles must go through this in order to exit. This is be done so that sediment that may be on the trucks that's in the site won't be out-tracked onto the loop and just cause disturbances outside. So we want to make sure that's all contained within. So by these driving over these vehicles driving over stones before they exit the sites. Another one was erosion control blankets. These will be placed over areas with slope sediment. We do not want stockpiles of sediment just exposed in the area. So in case like wind comes around and blows it away into the surrounding environment, you want to control that dust. So by having that on top, it can be covered and protected from the elements. Some more practices that we were using is sprinkling trucks. This is more of a process, having trucks spraying water on the ground. It will be spraying water on the ground of areas of exposed sediment. This will be so the water can weigh down the exposed soils so that airborne dust particles won't become a problem and will not be in the air causing pollution. Another process we had was riprap. This is an outlet protection device and energy dissipator. It can be used for our culvert, and also our bridge option is by placing stones at the exits of the culverts and by the bridge. This is really due so debris and trash, things that you don't want to be in a culvert, can be protected by using these stones, and will be good just protection devices. Another one we had with the picture is concrete washout containers. So when concrete is going to be used in our project, instead of just washing it off and let it spill all over to the environment causing a mess, we'll have these containers so it can be maintained and just be good housekeeping for the site. So when we're looking at our project, we want to determine what type of pollution sources that would be affecting it. The main one that we wanted to address was sediment. So a lot of those best management practices that I addressed earlier was really to how could we contain that sediment that can be produced on the site, and how can we keep it just in a good state and not have it just go everywhere. So this is one of our erosion control plans. Our construction is split into 3 phases. This was due so that construction can be done while also cars driving through the area can also be going through. So this is going to be one of 3 construction phases that we're doing. So this erosion control plan is used to visualize how our best management practices will be implemented onto the site. So as you can see, we have construction materials, storage, and sanitary portable toilets. These will just stay in the same location throughout each of the 3 phases and just will be used as good housekeeping measures. For phase 2, as you can see, this is where we're incorporating our silt fences. Specifically, it will be placed as a barrier between the outside of the road construction zones and between the native areas. So this will serve as a good barrier. So to protect some of that native soil that's there that won't be affected, and also containing that sediment, as I talked about earlier, so it can stay within the work zone and not be tracked out to other places. Also, you see we have our stabilized construction exits at the ends of the work zone so that all the vehicles that are leaving the site can leave through that, so all the sedimentation won't be out-tracked into the loop. Additionally, we have our riprap in the green. That is going to be our location of both the bridge and the culvert. So that is the location that we replace those stones to protect from such things, debris and trash. This is our phase 3. The difference between this one is to work on the other side of the road, the work zones are flipped. So this additionally makes our silt fencings will be moved to the other side of the road. And additionally, we have our riprap and our stabilized construction exit was relocated to adjust for the movement of the work zones. So that is it for the environmental. Now it's for the hydrology and hydraulics team to present their design.
Hello, my name is Noah Hernandez. I'm the team captain of the hydro team. These are my teammates Raymond Sanchez and Emmett Seals.
Okay, so this is the hydrology team, and we're doing a hydrology analysis. Hydrology is the study of how water flows to a site and structures to help mitigate and help that flow. So we need to know how the water is getting onto the site and how much water will be going into the site, and ways that we can do to prevent flooding and to mitigate that for the road. So for our scope, we will be doing that drainage analysis on the site using the SES unit hydrograph method. We'll be using this method compared to the rational method, which is also another popular method used. This is due because for drainage areas over 200 acres, it is required by the city of San Angelo to use the SES unit hydrograph method. So for our regulations, we'll be following the city's regulations. Specifically, we'll be following the City of San Angelo Stormwater Design Manual, and we'll be using HEC HMS, which is a computer software to help with our design. Additionally, we are proposing for 2 different options. We are designing for a covert option, and additionally, we will be designing for an open channel that will flow underneath our bridge to help bypass the flow under Foster Road. So as you see the map here, this is our drainage area map. So everything that you see in this map is all water that will potentially drain to Foster Road during a storm. As you see, it's a total of 877 acres, and as you also see, it's split up into different sections, 5 different drainage areas. This was separated due to many reasons, being land use was a good use, because from land use, depending what's the function of the land in this area, we have many things. There's families, streets, roads, parks, golf courses, and all various things that could help separate our drainage areas. Also, another reason we separated this way was for the flow. So as you see these lines, these are the lines that the flow direction will flow in. So we also kind of group those areas together of areas with similar flow paths. We helped use this. We got topographic data from SKG Engineering, and additionally areas that we didn't have data for. We used Google Earth, and that helped create our flow paths by using the maximum and minimum elevations from the area. There was a few drainage areas that we felt like we wanted to discuss. This was drainage area 1. This is actually our largest drainage area of the site, and additionally this composed of Bentwood Country Club. So Bentwood Country Club had a lot of multi-purposes things for land use, such as golf courses, parks, families, and then it was surrounded by a neighborhood. So we needed to consider that in our design. Additionally, at Bentwood, there are 3 ponds located, and when we went to a site visit to just see the surrounding area and how it looks, we noticed that there was a culvert from these 3 ponds that outletted flow to Foster Road. So we needed to consider that all this water that was going to these ponds from the surrounding area was outletting to Foster Road. So that was something we really had to consider for our area and, for all that flow, water. And then you see right there the location. Another drainage area that we thought was important was drainage area 4. This is the largest flow that goes directly into Foster Road. As I talked about earlier, drainage area 1 and the other drainage area 2, both of those flows go into 4, and this, so then you have the water from drainage area 1, drainage area 2, and 4, all going directly into the site. So it was a large concentration of water going into one area, and that was something we really had to look at and address. As you see from these pictures, the one below, this is a residential drive-through culvert that was placed. And it's located right here just at the outlet of where that water was coming from. This was ultimately going to be replaced in our design as the road's going to be widened. There's just not going to be enough space for this culvert to continue to be here. Also, as you see up top, that is the existing culvert that is at Foster Road that is carrying the flow, and that needed to be adjusted so we could properly control the flooding in the area.
So now that you guys understand like how the water flows through the site and how the topographic features affect how the water's going through it, we needed to actually apply these theoretical things to like engineering principles and use that quantifiable information. So in order to do that, we take flow paths, we gather information around the site and what kind of soil groups and how the land is, and put it into these equations of time of concentration and time to peak, and all these factors combine together to create what we need to ultimately get, which was that peak flow. So HEC-HMS is a modeling software that will basically take everything we had in Civil 30 and all those flow paths and where they conjoin and everything and make it a more realistic model. And so what we have here is the HEC-HMS model side by side with the drainage areas and the flow paths. And so what you'll see is we modeled our detention pond that we couldn't model in Civil 30 and accounted for it in the culvert after it, and all these thicker blue lines are kind of where sub-basins join together and like collect flow, ultimately going into Junction 3, which would be right at Foster Road at that existing culvert and the proposed culvert. And so what we did to run the analysis was we ran a 100-year storm, and it was a type 2 for the Texas region, and it would take readings every 10-minute interval for that storm in our HEC-HMS model. And so ultimately what that model does is it'll give us these hydrographs and give us what those predicted values for those flows will ultimately be. And so for our 100-year, you'll see on the top right in that square, the left orange square, that we have a peak discharge of 1459, and you also see it right here. And you'll see on these graphs when that peak flow occurred. So at the top of the peak is when that peak happened. So it would be 12 hours for the 100-year. And for the 2-year, which is the one on the right, that graph on the right, you'll see that the peak flow is around 490 CFS. And for COSA, Stormwater Design Manual, they require a 2-year and a 100-year design storm. And so that's what we did. And you'll see also when those times end. So for a 100-year, it'll be 33 hours. And then for the 2-year, end around like 3¼ hours. And so that would be the whole entire storm.
You can see our first our open channel design for the bridge. You can see right now, I don't know if y'all can see this, but there is a green line on the right picture that shows the existing flow from all these drainage areas that goes across the road. In blue, you could see how we're changing that. We're going to be changing this with drainage ditches and with the bridge and culvert. For the bridge, we had to move it about 50 feet north of the existing culvert, and we angled it about 20 degrees compared to the road. This was just to make sure that there was enough room for the riprap that we want to do at the outlet of the bridge. We chose to do an open channel design for this, and we made the bridge about 40 feet wide, and we made it concrete lined. Here you can see the proposed culvert design. We decided to choose 8 boxes, each being 4 feet by 5 feet and concrete lined. This one's moved about 100 feet north of the existing one, and it is at a 45-degree angle. Once again, we did this to make sure there was enough room in the right-of-way for riprap. This is able to handle the flow rate from all the drainage areas. It changes this slightly differently compared to the bridge, the flow. And it's also under the coastal standards, it's under 12 feet per second for a concrete line culvert. Here you can see the beginning of our drainage ditches. We decided to add drainage ditches in order to compensate for a 100-year storm. The left one you can see is the northmost drainage ditch. The goal was to try and make them with the right-of-way about trapezoidal and at a certain slope. Because of the restrictions we had, we restricted it to about 4 feet wide on the bottom width of this one. And the slope was too steep to be able to safely be left open. So because of the steepness of this slope, we had to apply some protections, we decided to use guardrails. These guardrails are supposed to help prevent people from crashing into these ditches. And on the right side, you can see the ditch that connects to the central ditch. This one's about 4 feet wide and 4 feet in depth. This one had to be rectangular due to the restrictions of the right. Here you can see the central drainage ditch. This drainage ditch contains all the water going into the culvert or the bridge. This one has a bottom width of 10 feet and it goes to about 40 feet wide on the top. This one does have the proper slope, which is according to TechStock standards, it is 1 foot per 3 feet tall per 1 foot. And that's the TechStock standard to not need a drainage protections in case someone can safely crash into this. It's 6 feet deep, and according to I believe coastal standards, for a concrete line channel, it needs to be under 20 feet per second, and ours is about 16 feet per second. Here you can see the south and south central drainage ditches. The left side is the south one. It's about 4 feet by 4.5 feet. This one was really difficult because with the right of way, as soon as you passed it, it was into a property, someone's house. So we had to really be restrictive with this one. Both of them are able to handle all the coastal standards and TechStock standards, and these will also need to have a guardrail. And I would like to give it to the transportation team.
Good afternoon, everyone. My name is Ibram Benitez, and I am the transportation team leader. On my team, I had Sydney Smith and Noah Hernandez.
So for the main scope of the transportation team, firstly, we wanted to design our Foster Road to begin on the south side of Loop 306 and then move all the way down to the intersection of Buckskin Drive. We wanted to reconstruct this road to meet a desired width of 64 feet. And we wanted it to include sidewalks, crosswalks, and potentially bike lanes. We would also raise the grades of these roads so that they could accommodate our new culvert and drainage designs, as well as including striping and signage for this new roadway. And we would also produce drawings for the site layout, as well as our pavement cross sections that we're gonna propose.
Here you can see the existing conditions for Foster Road. On the right picture, you can see the existing culvert. The bottom, you can see a picture of the road. This road varies from 20 to 50 feet because of the current road, on the north side being a 4-lane road, and on the south side being a 2-lane road. Flooding does occur at the culvert location, and so it's not able to handle the rain, and we will need to remove these whenever we widen the road. Here you can see the traffic study we did. For about 90 minutes, we counted the vehicles to try and determine the peak hour factor, which we found was to be between 425 and 525, to be about 150 cars coming in that hour. We also found from TechStock standards that the current amount of vehicles in 2018 was 1,476 vehicles a day. We tried to do a population group to update that to about 1,526 vehicles today for now. And the current speed limit was about 35 miles per hour. We later used these calculations for the ESAL calculations later. We'll talk about later on.
So for some of the design specifications, our road required it to be 64 feet wide. The inner 3 lanes would be 12 feet each, and the outer 2 lanes would each be at 14 feet. Sidewalks and crosswalks are required, and we went ahead and used this COSTA standard for that. No lighting is required per the COSTA street light policy in 2017, and no bike lanes are required but can be implemented if need be.
So the design standards that we followed, we used some from the city of San Angelo. These included our specifications for curb and gutter, the urban arterial street, concrete sidewalks, as well as the San Angelo MPO bicycle and pedestrian plan. We also use the pavement marking standards from the Texas Department of Transportation and the ASU guide for the design of pavement structures.
So now for our flexible pavement design variables. For our present serviceability index, we use 4.2. Anything above that was really used for highways and freeways. For our term serviceability index, we also use 2.0. There is an option to use 2.5, but that is also used for freeways and highways. For our delta PSI, which is the PSI minus the TSI, is 2.20. Our soil resilient modulus was 4 KSI. Our standard deviation was to be between 0.4 and 0.45, or 0.4 and 0.5, but we went ahead and used 0.45. For the reliability of our road, we went ahead and used 90%. Anything above that was also used for freeways and highways. This is just a common road. And for our 18 kip equivalent factor, we got 255,665, otherwise known as our ESAL. For our asphalt thickness, we use the astrographical method. This is the graph right here. So we inputted the variables that I just talked about into this graph right here, and it gave us a structural number of about 3.35. We later used an Excel precision checker, and we got 3.37. So after determining the structural number, we used the structural number formula, and we calculated our asphalt thickness to be 1.84 inches, but the COSA spec calls for 2 inches, so we had to use that. These are some of our cross sections that we drew out in Civil 3D. The top one is the current roadway cross section. It was determined that at the narrowest point of the road, each lane was 10 feet wide. It was also determined that the asphalt was also 1/2 inch, and that the base material underneath the road was 3 inches. The proposed road cross section, like I said, each side has to be 32 feet wide, 64 feet wide in total. We also implemented 6-foot sidewalks right here, and this gap right here had to be 3 feet between the curb and gutter and the sidewalk. Below the road, we had an 8-inch subbase, which varies for our road grade, and we also had a 12-inch base. Our final pavement thickness was 2 inches.
Here you can see the north end of Foster Road where the Loop 306 is. As you can see, it transitions from the 4-lane road to the 2-lane road, and there's not much to see. Here you can see our rendition of this, where we improve this to a 4-lane to a 5-lane road. We add crosswalks, sidewalks. We give it about 280 feet worth of taper when it transitions from the 5 to the 4. We provide signage for the yield turning lanes, and we include the 6-foot wide sidewalks. And we also do include, on the outer lanes, we will include, if need be, biking lanes so that the 14-lane road could be shared with bicyclists.
And for the south end of Foster Road, which would begin on the north side of Buckskin Drive, which was at Station 1, the saber link ended up being 285 feet, which did allow for a 64-foot width to be constructed, although it did merge from 4 lanes closer to Buckskin Drive down into 2 lanes. This striping plan was the reason we did this striping plan was that so drivers would be able to follow the road horizontal alignment. And as you can see here, we have a view of what the driver will see as they're traveling Foster Road.
So for our cut and fill volume of the proposed grading for our culvert, we use Civil 3D to determine this. We performed a vertical profile to simulate how much cut and fill we would need for this road grade. For our culvert, it was determined that it requires 3,758 cubic yards of fill and 861 cubic yards of cut material. If you subtract both of those, you get 2,897 cubic yards, and that is what is needed for a 6-foot road grade. This green line right here is the proposed, height of the road that we're proposing, and these purple lines right here, all along here, is the easements that the hydro team proposed. For the cut fill volume for the bridge, This option only required 2,471 cubic yards of fill and 662 cubic yards of cut. If you subtracted both of those, you got 1,810 cubic yards needed for material. And this road also closely followed the vertical profile of the culvert. I don't know if it's very visible, but here's the culvert right here. And then the purple lines also show the easements, or the depths of the easements needed. Drainage ditch, sorry. And for our final drawings, the picture on the left-hand side, we went ahead and implemented some crosswalks right here. This is a yield lane right here that turns onto the State Loop frontage road. And we also implemented this crosswalk right here, so that way people walking on this side can cross over to this side without any problem. We also implemented the speed limit signs right when you get into the road, so it's visible to the driver. And for the picture on the right, this is just a continuation of the roadway. This is section 1495, so it just starts again right up here. These signs right here, they're just there if in case a bike lane does want to be implemented, and also along right here. If y'all can see this right here, all along right here, this darker line, that is the guardrail that the hydro team was talking about. We had to run it all along the west side and part of the east side. And then the green lines right here represents the bridge, our proposed bridge. This is just another continuation of Foster Road. Here in this image right here is where our taper signage and markings begin. Starts off with the right lane end sign, and then it comes down about, I'd say 300 feet. And then it starts, the sign right here is where it lets the driver know that the lane begins to end and that they're about to merge left. This picture on the right is the ending of Foster Road, closest to Buckskin Drive. We implemented some crosswalk signs right here and the speed limit sign right here. These stop signs are already in place. And like Cindy was saying, this will taper down to 2 lanes, 1 in each direction. This is because there's nothing here right now, but later on in the San Angelo master plan, it will be developed to the urban arterial standards as well. And with that, we'll pass it off to the geotech team.
Okay, so hi everyone, I'm Lorenzo Dominguez. I was the team lead for the geotech team, and that's Ibram Benitez.
So for our scope of work, we were to design any abutments required. We were also to determine the existing conditions for the site. And we were also to write a soil report for our findings. Some of our design references that we used was the ASU LRFD bridge design specifications, the 9th edition. We also used the Foundations Design Principles and Practices book, textbook, and the SKG Engineering soil report provided to us. Some of the existing conditions, we looked at the soil stratigraphy. We determined this using the SKG geotechnical report, and we found that lean clay was below the roadway surface for about 15 feet. We also calculated the potential vertical rise. Our resource was the text designation text 124E, and our finding was that our PVR is 1.75 at the worst case scenario. Our reduction factor for this was whenever the flexible base would be placed over the existing soil.
So just to start out, we were deciding which flexible base material to use. So we just followed COSA specification 247, and it just pretty much had to meet all of these properties. Once we did that, we just determined that the engineered fill would also meet the same specification. After that, for our design for our abutment, we needed to determine all of our soil properties for the actual design. With the on-site soil, we ended up using these sources to determine those properties. And then for our fill material, we just followed the specifications for design properties. After that, we considered our loading conditions, one being the active pressure of the soil, the self-weight of the abutment as well as any surcharge loads above the substructure.
Some of the relevant specifications, our design was made so that it can meet the construction and post-construction loads. This design will also meet the geotechnical checks of overturning, sliding, middle third, bearing, and settlement. It'll also meet the structural checks of shear, sliding shear, and the corbel design for the seat of the abutment.
So pretty much after that, the way we started was, assuming that this is the current grade under the bridge, going from there to point A, we were kind of restricted with a 2.75 foot height, being one of our only real geometric constraints. And that was just due to the elevation of our roadway, as well as the girder and the slab and the bearing pad. So we had to meet that height. Everything else just kind of came shaped together after doing our checks for pretty much all of our geotech checks. So the first thing we did was to determine the active force of the soil acting on the abutment behind the wall due to the fill material. And the main way we did that was we pretty much just took a moment about point C, using the self-weight of the stem and the base of the abutment, and then the weight of the soil, as well as the active pressure. So once we determined that, it was, for all the self-weight, it was resisting overturning, while the driving were the active pressures. And all we needed to do after that was just the sum of the resisting over the sum of the driving just needed to be greater than 1.5. And then after that, we ended up checking for sliding, which was just a function of the normal force under the abutment as well as the frictional force under the abutment, using this equation, which is also a function of the foundation feed. Once we calculated that, we got a value of about 4, and it just had to be greater than 1.5. Following that, we did a bearing capacity check using Terzaghis method. We calculated an allowable bearing capacity of 6.14 KSF. After fully loading the bridge with, or not the bridge, the abutment with the bridge loads, we calculated it to be about 5.5 KSF, which was within our allowable. After that, we did a settlement check. We just used 0.5 for our total and our differential settlement. Then using Schmerman's method, which is a modulus-based settlement method, we ended up finding our total sediment to be 0.33 inches over a 100-year life cycle. And then once we did that, all those checks, we reloaded the bridge, or the abutment with the bridge loads and any surcharge load to make sure it still withstood those loads. And then once it did, we ended up with our final dimensions for our abutment itself, which led us into our structural design. So after we started that, we pretty much just determined that for the heel and the stem, they just needed minimal reinforcement. And then we ultimately just decided on number 10 bar at 18-inch spacing for both of those. For the seat of the abutment, we ended up designing it kind of like a corbel, which is pictured here. For our primary steel, which is this outside one, we determined it to be a number 10 at 18-inch spacing. And then within the ASU LRFD bridge specifications, it specifies that if you have a primary steel of a number 10, you must use number 3 bars as the ties. So then after we calculated the spacing for that, we just got at 12-inch spacing. And then that's our image of our final dimensions for our abutment. And I'll pass it off to the structural team.
Hello, everyone. I'm Raymond Sanchez. I'm the structural lead, and this is Drew Dykes, my team member. And we will be covering our steel bridge alternative to the final culvert design. And so for our scope, we wanted to propose a steel bridge that would meet all of the demands of the culvert. So that meant 100-year storm peak flow, being able to convey that under the bridge, as well as some of the other scopes being that the bridge we wanted to design is much like this one. It would just be one single span, So when I say simple span, simply supported, it would just be one being linked along the link. We use a program, it's called LRFD Simon, and it's made specifically for simply supported short span bridges, steel bridges, and it'll run all ASHTO standards and make sure it's verified and compliant. And finally, we wanted to produce professional bridge drawings and details. And so here are some of the design references we use for our design. As I said before, we use a program called LRFD Simon, and that'll be what we use to design the steel bridge. And then we use the AISC Steel Construction Manual to help us select a preliminary beam size. And then we use the LRFD bridge design specifications, like the geotech team, to account for any ASHTO standards and anything like that for our loads. So some design constraints for our steel bridge, like I said before, according to the COSA standards, we needed to have that bridge convey that 100-year storm underneath. And with that, we made sure to design for a 1-foot freeboard under the lowest part of the bridge. And so what that means is just that at the top point of the water flow going underneath has to be at least a foot to the lowest part of the bridge. And so that would just prevent any damage to the bridge. And so for the way the natural flow of the water goes through our site, it kind of goes at an angle across the bridge, and the culverts that are actually there right now are a little skewed. And to keep that consistent, we kept it skewed for our bridge itself. And that would just help any hydrologic forces that would hit the abutment and like kind of mitigate some of that damage. And ultimately, we went and we wanted some aesthetics and construction speed. As Drew mentioned previously, this is the only means of access to Foster Road. So a steel bridge is it's not as bulky as a concrete bridge, and it looks nicer typically. And another design or a construction thing that you could do for a steel bridge is called accelerated bridge construction, so ABC, and it allows you to basically create the entire bridge off-site and just put it in and just set it down, and it's super fast, and it increases the construction speed by a whole lot. And so what is LRFD Simon, this program I'm talking about? It's a program. It was developed by National Steel Bridge Alliance, and like I said, it accounts for any ASHTO standards that would help create a successful bridge design, and accepts all these user-defined loads. And what you do is you input any geometry, like I was saying, like your steel beams and concrete decking slab. You input it into it, and then it'll run an analysis and check it and ensure that your design is actually compliant with your single span bridge. And if it's not, then it'll just it'll request the user to update the geometry until that compliance is met. And so here are just some of the user-defined loads that we put into LRFD Simon to help it do its analysis. And so we have a load of 686 pound per foot. This was calculated, and it's just the dead load, so dead load being the weight of the beam and the weight of the concrete just by itself with nothing on top of it. And that was we used a 0.64 kip per foot load, and this was actually a lane live load that's distributed over the width of the lane itself, so that would be 10 feet, and that's just kind of a number used for regular traffic. And then finally, we use a 750 pound per foot load, and this was to account for those sidewalks that are going along the length of the bridge, and it's roughly about 5 or 6 people worth of pound per foot that you would just apply into LRFD Simon as well. And now pass it to Drew Dykes to talk about our design truck.
All right, so the way that the LRFD Simon tested the bridge was using ASHTO LRFD's design truck and design tandem. And so it would run a simulation which basically acts as moving a design truck across the length of the bridge, and it calculates the highest moments shears. But it runs it as if it was a line. And so all of these load combinations are running on a line girder, but we know that a bridge isn't a line because it has width. And so it uses the design tandem to account for the other girders across the width of the bridge, and it runs this transversely. And it spits out a distribution factor, and it applies it to your loads longitudinally, and it gives you your results. And so here is the image of our bridge drawing and layout. We use the W16 by 100 beam, and it's spaced 8 beams across the 83-foot width with 3 feet of overhang on each side, as well as a cross diaphragm at mid-span. Detail A is a depiction of how our rolled beam will attach to the concrete decking with shear studs, and then those dimensions. And then this is the cross-section of our bridge at the abutment. This is how the deck is attached to the beams, which are sitting on the bearing pads, which are sitting on the abutment. And detail A is just the dimensions of our beam selection, the W16 by 100. In detail B, it's showing our concrete reinforcement design. After our calculations, we found that both longitudinally and transversely in the concrete slab, we would be using number 5 bars at 6-inch spacing. And we compared this to a similar bridge project we found, and they use similar numbers. And there is, detail C is also a side view of what our beams look like with the shear studs attached.
So ultimately, once we do the entire analysis, we get these results, and we plotted these results on these graphs here. And what they are is, on the left is a shear envelope, and on the right here is a moment envelope. And if you look on this x-axis for both, they're, as we stated before, the truck will drive along the length of the bridge. And so you want to have these points, these data points taken every 10th increment. And so that's what that x-axis is. And for our y-axis on our shear is in kips, so 1,000 pounds, and moments is in kip feet. And so for our shear diagram, you see we have 4 lines here. These two, this upper one and this lower one, are our live loads, and so that's our truck running the length of the bridge. And then the middle ones are just, for example, the orange one is a composite dead load, so that's just, as I was saying before, the slab with the steel beam together only, with nothing else on it. And so I just want you to notice that these two control the bridge, and so that's what we've designed for. And it starts on one support, and it'll be the greatest, and then as it's going to the next support, the shear will turn negative and linearly go down. For a moment, as the truck is driving along the length as well, you'll notice that it also controls the live load. It's producing the most moment on the bridge. And since it's simply supported simple span, it's only gonna have positive moment. It won't have any negative moment because if you had 2 spans, it might create negative moment as it's driving along that length. And so that's the main thing I wanted y'all to see. And LRFD Simon did verify that all of our design was correct and that the bridge was successful and acceptable. And so with that, I'll hand it to the construction team.
Hi everyone, again my name is Sydney Smith, and I was the leader for the construction portion of our design, and I worked with Drew, who was a team member. So for the scope of our construction, we began with creating a Gantt chart using Microsoft Projects for all of our divided teams to keep up with the tasks that they needed to complete. We then produced a construction schedule that we actually did 2 that would account for either the culvert inclusion of one of the designs and one with the bridge design. We found all of our permits that were required before construction could begin. We outlined a phase plan for all of the traffic control that we would be using throughout this process. We analyzed different costs that we could have used to figure out what our actual total construction costs were going to be for both of our project scenarios. Okay, so here we can see the team Gantt chart that we all used. We use Microsoft projects for this, like I just said, so every team is color coordinated to match up with the calendar on the right side. So we have, on this chart, we have the team, the tasks that they needed to complete, as well as the duration and the start date. And over on the calendar, you could also see how, track the progression of how long each task was taking over this course, and to just make sure that we stayed on track of everything. Again, with the construction schedule for the project with the design of a culvert, we used Microsoft projects once again. This made it pretty easy to kind of keep track of our durations and how long we would take to complete everything. I mean, you can't see it, but there's a calendar again on the other side. And it also includes our general conditions. It starts with the bidding and letting process, and then moving to phase 1 through 3, which Drew's gonna explain here in a second, as well as our landscaping plans and our final acceptance. And this project did end up taking, we found, a total time of 270 days, which was about 8 to 9 months.
I also just wanted to state that it appears we're having some technical difficulties. These are supposed to be some videos of our, so if you want to see our construction phase plan listed out, as well as our Gantt chart, it is in the appendix in the report, the construction report appendix in the back.
So again, we have the same outline for the construction schedule with our bridge. It's literally the same format, we just have different tasks to be completed for the construction of the bridge, but generally everything is almost the same besides these tasks for the bridge portion. We did end up getting a final construction time of 275 days for this project, and again, that was about 8 to 9 months. We did expect it to be a lot longer until we decided that we would do the ABC for the bridge, so that did give us almost the same time frame as it would take for our culvert to be constructed.
And so this is just a visual of how we decided to set up our phase plans. So this was kind of a tricky bit for our construction team because we had to figure out a way to create a phase plan for construction while maintaining the road staying open to traffic, considering that it's the only road accessible by the residents out there. So as you can see from this image, we set up in the first phase, we needed to widen the road on the left side, and we widened it all the way up. That way we could come back and be able to have enough room to work on the right side while allowing traffic to stay on the left side. And so going to phase 2, the road has been widened on the left side, and we set up the TCP to where the traffic will be routed up that left side of the road, and the work zone is on the right. And as you can see here, we are installing half of the bridge on this side, as well as completing all of the road work on that side of the road. In phase 3, we switch sides, and now this bit of road has been constructed to where there's enough for 2 12-foot lanes, so we can remove the temporary traffic lights and signaling that we had north and south on site and open it up for travel. And we will construct the left side of the road as long as that second half of the bridge or hydraulic structure.
And moving on to the permitting for our project, here we just created a table that would kind of make it easier to recognize. So we've got our permit type as well as the agency that we need to contact to get certification for this. Beginning with the Texas Commission on Environmental Quality, we would need a general construction permit, and we need to acquire a lane closure permit, contractor registration, concrete testing on site from the city of San Angelo. And from the Environmental Protection Agency, we would need to get with them to make sure that we are following everything that we need to appropriately account for the Clean Water Act and the Clean Air Act. And we would also need our environmental inspection from the Stormwater Protection Plan, the SWIP. Okay, so for our traffic control plans, Drew just kind of outlined everything, but we use all of our standards from the Texas Department of Transportation. This includes our work zone signing, our traffic control for one lane, 2-way traffic control, as well as our pavement markings, our barricades, and our bridge and details. Moving on finally to the total cost estimate, we're going to start with our bridge design. So as you can see here, we have the total cost estimate, and then we have a small clip of just like a zoom of a few of the items that can be located here. The outline of this chart is basically just like the bid item code, the bid details, as well as the unit quantities and the total cost per unit. So putting all this together, we came out with a total cost estimate of $12.495 million. And then we used the same kind of format for the culvert design estimate. The items here have been changed for the most part, and then again here you can see a clip of a few of them. So basically the breakdown of this for the quantities, we hand calculated the majority of them, and for a few that we had a lot of trouble with, we used, I believe it's the bid item unit dashboard from TxDOT to use the maximum quantity for the San Angelo area. And with those quantities, we added on 5% so that we could account for extra costs, as well as for the price per unit. We took all of these, the high average cost for, or from the TxDOT bid item unit dashboard, and together we got a total construction cost of $11.94 million.
And that concludes our presentation. Any questions? Yes, Jordan.
Can I go first?
Sure
Okay.
thing.
So your northern tie-in, I didn't see it in the traffic control. It looks like you guys kind of left that part out because it was gonna get sticky. But it does look like you go all the way to the loop frontage road
Yes, ma'am.
with your design, but I didn't see that in the traffic control because all your signage was set up south of that. But how would you plan on constructing that?
Are you talking about this part right here?
Yes, like all,
Okay.
everything north, like in that.
Yeah, so this area is actually the width that we are going to taper down to. There's a joint right here in the
Okay.
existing road.
So you're
And
just gonna
so we're-
restripe it?
Yes,
Okay.
well, yes, ma'am. We're gonna restripe it, we're also going to put the crosswalks and
Okay.
all that.
What's is that a two-way frontage road or a one-way frontage road at that point?
It will be, we're gonna do one lane, but we're gonna extend it so that we can have 2 lanes of travel. on
No,
just
the
one.
frontage road.
Oh,
Yeah, so right here.
Is that one way or two-way?
One way.
that's a one
I
way.
think it's one.
And you didn't have a need for a left-hand turn onto that from the? You don't have a turning lane in your final design, correct?
Oh,
A turning lane from the front.
From northbound,
I believe so.
from northbound, what's the street, Foster Road?
Foster Road.
From northbound Foster Road,
No.
to westbound on the frontage road.
To westbound, well, it's
Turning onto the bridge.
there's one way traffic right there.
Well, that's what I just asked, is the frontage road one-way traffic?
Oh, yes,
Oh,
yes.
I'm sorry, I thought you meant Dairy, okay.
Right, you said two-way, and then I asked.
Got it with the, like, Foster
All right, all
Road,
right.
not frontage.
Okay.
Yes, sir.
My name is Zephyr Mendoza, I'm with the city of San Angelo.
Okay.
One thing I did have a question is, in your calculations, well, geotechnical wise, in the report, was there any groundwater noted in the report?
No, there was no groundwater noted in the report.
No groundwater in the report?
Yeah.
Okay, so you're adding six feet of fill?
Yeah.
Is there gonna be groundwater then? Is there gonna be groundwater, and how does that, was that even accounted for in your abutment calculation?
So what we ended up having was that on both sides of the, like, you have the abutment and then behind it with the road.
Okay.
On both sides, it's concrete lined, so I just kind of figured that, since there was no groundwater noted before, and we're basically making it almost like a
So the
concrete
study
lot.
didn't account for groundwater, it just said none was noted at the time?
Yeah.
Okay.
So I think like groundwater study would be needed.
Okay. I also have another question regarding the abutment and construction phasing, if I can sneak in, sorry. Is the abutment proposed to be one solid piece for your steel bridge, or is it supposed to be 2 separate abutments? Because Foster Road, as you noted at the beginning, is a one-way feed into Butler Farm.
Right.
So how does that work for construction if you have to construct that entire piece?
Oops.
Okay. Well, the way that we designed, this part of our construction phase plan is so that we could lay, 4 beams out of our 8 and construct half of the road across.
Yeah, but the question is, did you design the abutment to be phased and constructed in 2 pieces or just one?
Just one.
Right.
Right.
And so related to that, how are you crossing, so the eastbound, the 2 lanes of traffic in phase 1 are gonna be eastbound, are gonna be in use, right? I mean, on the east, sorry, not eastbound, the east side of Foster Road is gonna carry both directions of travel in phase 1, right?
Yes.
So how are you crossing the existing drainage during that period of time, when there's no bridge or no culvert?
How are you crossing the drainage, is what you're asking?
Yeah, so go back 1 slide.
Okay.
So where you have the bridge right now?
Right.
Right? So, in phase 1,
Yes.
So
we had
in
planned.
phase 1, you're widening the west side of Foster Road, and in phase 2, the traffic's on the west side, right?
Yes, sir.
Are you installing the bridge on the?
So the bridge we have moved, so the low point in our road is where our current culvert exists.
Right.
We have moved the proposed drainage structure
Right.
like 50 feet north,
Okay.
so that we can keep the existing culvert in place during construction.
Okay.
That was our plan.
So there's
We
no
didn't-
grade,
We didn't show it here.
there's no significant grade, well, there's some grade change there.
Well, there's
but-
some pretty big grade change there, but.
But in phase 1,
Phase
the
1.
traffic's on the left-hand side,
Yes,
correct?
traffic. Yes, sir.
Okay.
No,
So
phase one traffic's on the right-hand side, we widen the left-hand side,
So if you're raising the road 6 feet,
yes.
how are you gonna build that when traffic is way down here? Are you gonna have a huge, like, are you gonna use special shoring or something to hold up all of that dirt that you're building the road up?
That is some of the things that we looked into,
That's a means and method the constructor would be responsible for, right?
That's you, buddy.
Oh, somebody saved him.
It will affect your bid prices.
right.
Yeah.
So your 12.9 and your 11.94, it affects it.
Right.
Especially with the phasing of construction too versus one bridge. You're talking about an ABC bridge, where you bring it into 2 pieces.
Right.
Steel bridge versus concrete, because
That's.
you can construct the same thing as the concrete.
Mhm.
So those are some things to consider. As well, since you're raising 6 foot, the next question I had is,
Are you buying
No.
right away?
huh?
I said, are you buying right away? No.
Yeah.
You're raising it that much, are you buying right away if you're widening the road that much?
Correct.
Well,
Right
that
away
is-
from mine.
that is-
Mine had to do with the raising, but I'll let you go ahead and
No,
answer.
no.
Ask that one. But, the hydro team had specifically mentioned a guardrail. The placement of the guardrail, from what I understood in your presentation, is between the curb and the, where is that located at?
It'll be between the curb and gutter and the sidewalk, so there's a 3-foot spacing.
Okay.
Required.
So
according
you're
to the
raising
test
it
specs.
6 foot, and then
Yes,
you
sir.
have a pedestrian path, and then I'm assuming your slope going down into these proposed side drainage ditches, there's a safety element there.
That's right.
So you have this large transition that Butler Farms, if somebody is walking there, or, you know, within a rascal or whatever you wanna call it, they could injure themselves. So there's a consideration for both sides of those to have handrails.
Yes, sir.
Yeah.
Or maybe you relocate the guardrail. Just look at that in consideration, that's a safety issue too as well, I'm going to point that out.
So,
Okay, go ahead.
You said your bridge was a steel bridge, but then you also had drawings that had is it a composite bridge or is it a steel bridge?
It's a composite bridge, it's a steel
Okay.
composite bridge.
Okay, well, a steel bridge with a concrete deck is different than a composite bridge.
Okay,
Right? I
so
mean, the loads are different, the design's different, so is it a composite bridge or
It's
is
a
it?
composite
Okay.
bridge.
Well, you need to get your language straight there,
Right.
because
Yes, sir.
it's not a steel bridge, it's a composite bridge, right?
Okay.
Okay. Which makes sense, that's a good
Yeah.
plan, right?
Yes, sir.
Yeah, I'm gonna get you on the abutments too. So I saw stuff about stone riprap in there, and I saw corbels, and I saw a stub abutment, and I'm just, kind of confused. Where are you putting the riprap? I also saw that in the analysis, you did a hydro analysis with stone riprap in the channel?
I don't believe the analysis, did we put riprap in the hydro analysis?
The only place where riprap is, as far as I know, is on the outlet, after it goes through the culvert or the bridge. Because right now, there's existing riprap to direct it into the current drainage outlet, the natural drainage. We just wanted to copy that and bring it down to where, bring it up to where our proposed one would be.
Okay. So with the bridge, is it a stub abutment?
Probably have to refer to our geotech team.
Yeah. I noticed that the structural engineers had the geotech do the hardest structural design. Just saying.
I agree with that. This is why we're proposing a installable box culvert, and the bridge was just an alternate.
Yeah, that's fine.
So you guys are recommending the culverts versus the bridges? We didn't catch that at the end.
Right.
Yeah.
Right. Well, yeah.
It's definitely cheaper.
100%
Easier. Yes.
You still gotta answer the question.
Yeah.
Well, show us one of those cross sections. One of the abutment ones, anyone.
Also, I'm gonna nitpick on you a little bit here. All new bridge designs need to have a scour analysis done with them as well. Did you guys take a look at the HEC and how your flooding events would affect, localized scour around the abutments, the shallow foundation abutments?
Not specifically in.
Especially if you're changing the course of the natural stream right now, you're moving it down, so.
That makes sense. I didn't think about that though. And
We wanna see the abutment cross section. Not that one. Yeah. So you have this one, and then go to the next one. Go forward one slide. All right, and then you show this corbel, so which one is it? And that's one of the, I think that's the first question.
So this isn't, our design, it's just an example of what one looks like.
How to design
Yeah.
the shear reinforcement for that? Okay,
Yeah.
so go back one slide. So this is the
That's
design.
final. Yes, sir.
Okay, so that answers one question.
Okay.
Yeah, 1 foot of, I tell you, even for any scour, I realize, I'll just say scour is out of the scope of your project to be nice. But 1 foot is, for that, I don't care where you're going, 1 foot is not gonna cover scour in that, so just remember, scour in the back of your mind next time you have to deal with a bridge.
Question on the hydraulic analysis. Did you guys consider a fully developed upstream, or did you guys consider as-is conditions?
According to this coastal development map, we tried, with everything that was already built, we just tried copy and pasting what they had in there. So for example, there was, I can't remember the name of it, but there's like a house is being built in drainage area 5. We tried pretending that all the houses were built, and there was no, it just said commercial. We really didn't have anything to guess off. So what we did do is we guessed off of the things we used in drainage area 2 to say, we just assumed it would be similar to that.
And
So I didn't under, you did or did not assume that it was all
Yes, we did.
developed?
So,
Or
yeah.
partly,
Yes.
all
Sure,
developed or
yes.
partly developed?
We fully developed.
Okay, thank you.
Okay. And then another question, did you guys do any analysis as to the level of storm event versus the cost? So say you've got a 100-year storm event at over 20 million. What happens if you guys handle a 25 or 50-year event and the cost is a third of that? Did you guys do any analysis, economic analysis for the bang for your buck?
We didn't do a specific economic analysis on the hydro studies themselves.
Yes, sir.
So, I've got one more, then I'll leave you guys alone, and I'll pick at you later, because I got more. Why in every plan view is the culvert draining onto the roadway, and how is water getting through it?
Plan view?
Are you referring to the one that was in the hydro slides?
Every time you showed the culvert,
Yeah.
it's oriented wrong.
Just show it.
Which
Probably
construction?
That's bridge, let's keep going, keep going. That's bridge, right?
That is bridge, that's not culvert.
Yeah, just go back to your hydro stuff.
That's a lot of clicks in it.
Yeah.
Is there a restart button?
I don't know.
It's hard to tell, but there's this little green orange part.
Yeah, normally you show the intermediate walls going with the flow, and all your shorter lines, those are your intermediate walls. They're aligned with the roadway as opposed to the channel.
Well, the red's,
It might
is the
be-
red the bridge or the culvert?
It might be the quality of the image on here, but I'm pretty sure we drew the lines in the direction of the flow.
So if you're looking at the road, if you're standing at this end of the road and staring directly at it, the culverts will be at a 45-degree angle if you're looking at it from there. So it does accommodate for the flow, I believe. You can see like
The orange is the proposed culvert.
yeah, I guess you should have zoomed in more.
Well, well, I'll stop, now we're talking about.
Another issue we have is we have water coming from the north up here and a lot of water coming from the south. So, I mean, there was no real perfect way to collect all the water with the angle.
Hey Drew, kind of a combo question or suggestion with hydraulics and transportation. There's a lot of guardrail, which people tend to hit, and then you gotta maintain that. Did y'all ever consider like a storm sewer system? That way you wouldn't have as steep of a slope, and then if you added 2 feet to your sidewalk, then that could be shared use for bicycles too, so you could kind of solve a lot of issues that way.
Right. I think the hydrology situation kind of comes down to the right-of-way that we were allowed to work in. So we have 100 foot of right-of-way. The road comes out to 83 feet. We wanted to propose a sewer system. We thought about that, but the pipe that would need to outlet, so, yeah, to the river. So there's a culvert on the loop further northeast from our side where the water from Foster Road eventually drains into. And so we thought about maybe a sewage system running some pipe through there, but then we'd have to go outside of our right-of-way and try to like get a drainage easement of some sort. And so we felt as though we kind of did the best that we could in the hydrology area with the time that we had and the right-of-way that we had.
Yeah, so to comment on that for, future thought, I've seen a lot of projects where people would try to avoid takings of right-of-ways, where that was the right solution, because it is hard and it's politically hard. So I think it's really, really important I understand for the scope of this project why you wanted to stick to the right-of-way you had. But I would caution you as you future engineers to really think about that, because there's many cases, especially as you get in more urban environments, that's by far the best solution. And I've even seen takings at an airport, right, where they actually took, part of the airport property in order to get an intersection to work well, and it is clearly the right solution. So don't cast those out of hand in the future, and the thing is to go to the right people and start preparing the battle to do that. Because if it's the right solution, you really should look at it.
We did.
You're showing a drainage easement, right? So I think part of what you haven't fully conveyed is that you're gonna tell the city they need to pursue acquisition of easements.
That's definitely a recommendation that we would make for pretty much every single aspect of this project.
The only reason why the central drainage district was feasible just because we assumed that the drainage easement that was requested by SKG was actually gone, because there was no way of holding that much water within, I think, 3 feet of road, I think is we have, a 3 feet of right of way, which we had for that
one drainage ditch?
Yeah, there's some
Which is the
30-foot
purple line.
drainage easement that was included in the data file that we received from SKG. And so.
So you assume
I
that
think
was there.
that one's to be attained, but
But you still want, you might have done a different solution if you had more, is what you're saying.
Yes.
Okay, yeah. Well, like I say, just as future reference, I mean, don't just take it, and,
Well,
I mean, if the right engineering solution is something that requires somebody else to do something, you at least gotta go ask them. You're not gonna win the battle all the time, but.
We actually, for the sake of realism, reached out to some of the property owners, and
Yeah.
one of those guys said, that would not benefit my land, so.
Yeah, that's not the way to do it. Especially in Texas.
Yeah.
So.
Yes, George.
Thank you. So I saw that you have curb, but no storm sewer, so is it like a slotted curb and you have a sawtooth profile and we're getting the water off the road that way, or how are you getting the water off the road?
Are you referring to like down here?
No, she's
No,
referring
the
to
actual
curb and
road.
gutters.
The curb and gutter.
Yeah.
That's
and
something
gutter.
that we would probably implement over the bridge. That
So
is
you're
an
only gonna
option.
have one drainage point on this road? At the bridge?
We didn't necessarily account for drainage on the actual road.
Okay, so you're gonna increase all this impervious area, right?
Yes.
And have no basically ditches, so to speak. And then we're just gonna hope the road doesn't flood?
So that's,
I don't like that at all.
I imagine there would be some weep holes down into the drainage ditches of some sort.
Well,
That's
You
what,
would assume?
that's what we would assume. That's what we should have done. That's
what we should have done, yes.
Slotted curb is a thing if you don't wanna do storm sewer.
What is
but
it called?
Slotted curb?
Slotted curb.
Yeah. And it'll let it run off into the ditches, but again, you don't have hardly any ditches to speak of because you jacked this roadway up, right? I don't know if we have flooding problems out there right now, but usually whenever you make the curb and gutter roads, you depress the road so that it drains over the back of the curb and then you have storm sewer. But I don't know what your ditch capacity is, to account for all of this water that you're gonna hold in your ditches, but I'm feeling it's all gonna start going off of the right of way and then landowners are gonna get really mad at you.
Are you talking about the drainage ditches?
Could you bring up your profile and we can kind of show you?
Yeah.
The beauty of it is you're elevated, so you have no off-site drainage going to your street. City ordinance says 6 inches for the 2-year event and 12 inches for the 100-year event. So you could evaluate that, and you probably don't exceed those for within the segment of your street that you're having to peel it off ever so often, so. Jordan's point, you're gonna have some point in there, you've gotta relieve it. So it's a further evaluation.
Yeah, and I don't know what the profile does of that road, which way it's going.
Go to the vertical profile. Transportation.
I guess you guys didn't get to the point of having a full plan profile sheet within your design drawing, so I know time snuck up, and there was a lot to this project.
Oh, yeah, it's a pretty robust project.
It is,
It's like-
good job, but.
Yeah.
I
There you go.
I thought you guys were doing what you did, yeah.
So, I guess, if we were to go back, we would implement what was it, the curb?
Slotted.
Slotted curb.
You can see those around town. I mean,
Yeah.
as you drive around town now, you're gonna go, oh, that's a slotted curb.
Yeah.
This is the side closest to, the State Loop 306, and then this side over here this is where Buckskin Drive begins.
Yeah.
So, it's just the location of the culvert and the bridge.
I think half the reason why we had our road so high was just because of how much room we needed to make the depth of the drainage ditches.
Yeah.
Yeah. That's the only reason it was really 6 foot high. But yeah, theoretically it would drain right here, around this point right here with those curves.
I think,
All right, I'm sorry, since we got onto the subject of drainage, I was gonna let it go. We gotta talk about your bridge joints.
Oh, no.
Okay,
So you've got steel,
yes.
and you're going to be washing all the water down towards the bridge. Water's gotta go somewhere.
Yeah.
You want your joints to hold, but we know they don't. Now you're washing it over the steel.
Are you assuming that the flow going under the bridge will reach up to the
No.
top?
I'm
No.
I'm talking about the water onto the
We're
road.
talking about the drainage from the catchment of the road itself, right?
Yep.
Right.
Drainage on bridge decks is a big conversation right
Yeah.
now.
Right.
And so you didn't include that in your design, okay? So the things you gotta worry about there are, one, how are you gonna get it off, and when you get it off, what's it gonna do, right? So are you taking it directly into your, because the main drainage is coming from the west to the east, right?
Yes.
So if you're dumping it to the west, then you gotta dump it into your drainage system, you have to account for that. If you dump to the east, where's it going? Because did you design, I mean, how much did you design on the downstream side meters? Did you do any design on the downstream side?
Ran out of room.
Right, and so if you're gonna, the issue there is, you're gonna dump it there, and that's now you could inundate somebody's property. So, there's always lots of things that you don't cover in these, so.
It was, I think when we did view how the flow paths work for the area east of the road, almost none of them went north towards our area, they went east, like they didn't.
Yeah, I understand that. But just like you accounted for the development of all the area upstream from you when you did your flows, well, you're creating, the road itself creates an increase of storm runoff for the people downstream of you, and that's not in the project, right?
Right.
So,
In
okay.
your bridge design, there's a local bat population not far. Did you plan for over bat housing in this one?
Woo! Was that in your scope?
What's the time, Dr. Benz?
Can you go to your design for your pavement cross sections? That's transfer.
He did the surface. Yeah.
Wait,
Uh-oh, you wanna get in it?
oh no.
You saw it?
Well, talking about the pavement cross section.
Yeah.
So, you noted that you have lots of studies underneath for the SKG report.
Yes, sir.
Was any consideration taken in treating the sub-base for that? This blade has a shrink swell factor, right?
Yes, sir.
And then we noted that groundwater wasn't noted in there, but a groundwater study should be completed. So that's something to take into consideration when you're, and it's not pointing you guys out into the geotech, but just something. When you go there, because groundwater is just pretty big.
At 6 feet, the swell is not gonna.
Well, I'm talking about the other parts of the road.
So we actually,
It's 19, we don't have to treat it.
Yeah.
so we actually met with Reese Albert about this issue,
Okay.
and they recommended that we do a lime softening.
But when we looked at the COSA spec, it really only said like, if the PI was over 20 to do it, and we ended up having 19.
That's what I was looking for.
Woo! He shoots, he scores!
Pass it off to you. You're welcome.
So before we close, I want to ask the question I always want to get to. So, what are the biggest things that you took away from doing this project? What are the biggest things you learned in this project? If you all would each individually respond to that, that'd be great.
I learned that drainage areas are huge.
I think like you guys have been telling us, we didn't account for a lot of things. So I guess I knew a lot goes into stuff like this, but I didn't realize how much like critical thinking it takes. But this really like opened my eyes to that. So
I've never had like a project manager role, so learning to work with different people and different skill sets can be kind of challenging. Probably my biggest takeaway.
I guess for me, definitely talk to people and get, people that are informed about all this stuff. So mentors, teachers, like really get yourself out there and learn as much as you can is what I took away from this. And just make sure to apply those things whenever you can so you can continue growing your knowledge. That's what I learned for sure.
What I learned? Really proud of my team. I like to say that. They worked really hard and I'm the best. The actual stuff, I feel like communication was really good. Me and Raymond, well, Noah was our team captain for hydro, but he didn't take the class yet. So me and Raymond were kind of mentoring him how to do it, and then at the end he was able to try to answer some of y'all's questions. So I showed us like really the development of us communication, not divide and conquer, and just actually help each other out. Another thing was the software. When we first joined them, doing those drainage areas, kind of relied too much on the software, I would say. So I think the software is really good, it helps a lot, but using your own engineering judgment to help it assist you
Very good.
can help. That's all I got.
I think for me, the biggest thing would just be like, there's still a lot more to learn. Like, even just with like this project, kind of like what you were talking about, the scouring and stuff. There was also like a point where I really wanted to try and take the leap and try and do like a pile foundation instead, because in my mind that just kind of sounded better, and it probably is, but I ran into time constraints, which ultimately me just relying on what I knew how to do.
Yeah, I understand. It takes a lot more, but it's highly unusual these days to put, you know, like a stub type of abutment in.
Yeah, I could tell because when I was looking for stuff to kind of look similar, it was really hard. So I was like, something's not right, but I gotta push through and design the best I can.
For me, I think the number one thing that I learned best was to time manage. Each team had some portion of the work to do, and without their work, some other teams couldn't get started. So time management was a big factor into our project. Communication was also huge. Without communication, you don't really have anything. And then also going back to Emmett's comment about the software, I've never used Civil 3D. So these drawings right here and the alignments that we made, the vertical profiles, all that, YouTube helped out a lot in helping us make all these drawings and all that.
Just to reinforce what he's saying, one big thing I think we all realized was how everything layers on top of each other. Hydro had to get something done so that transportation could, so that geotech could, and then it kept cycling back and forth, or each of us had to get something so someone else could work on something.
But you guys did a really thorough job of this project. I'm really pleased with that. I've never been in a senior project where you don't get questions about stuff that either wasn't in the scope or you didn't think about. So I would take those as lessons to learn and not as necessarily criticisms. Maybe a few of them are criticism of your work, but most of it's just other stuff. So I'd like to commend you on a really good project.
Thank you. Thank you.
I promised my team only 30 minutes of torture. So time is over, you have to torture them on your own time. Mr. Gully, would you like to say anything else, being kind of our main client?
Oh, it was a pleasure to meet and work and grow with the whole team and answer questions and challenge them, really. It was fun just to have this young energy coming in and challenging them to think, and really, you know, your mind is your muscle that you're gonna carry forward and you're gonna be successful with, so just keep it sharp and pursue learning every day. And like you talked about, reaching out to those mentors and those engineers that have been out there and done that and may have made a mistake or two.
And your contractors.
And your
They're
contractors.
pretty good contractors. Sometimes.
Well, thank you very much. Thank you all for coming. It's been a pleasure as always. We'll see you next fall. And don't take some food before you leave. Thank you.
Oh, man, doing all right. Hanging in there. Really recognize she's all cleaned up and everything. I know. It's weird. I don't do it often. Yeah.
So, bro, you dog, you got me. I'm not sure who's collecting, but I'm not sure who's serious. You got me. Oh, hey,
First time. You can tell.
Thank you, sir. Yep. Did you borrow that from us? Okay, I'll get it back to whoever it belongs to.
Well, time to go back to the office. Yep, I'm gonna go say hi to Drew.
We won't say anything.
Did I end the live stream?
Yeah, it is now.
Oh, you still going?
Yeah.
Thank you for coming.
Thank you everyone for coming to the live stream. We're gonna end it.
I felt it was pretty good. I liked it. It's part of the
I like
we talked about that ditch on the other side, and it finally came out.